Well, hello everybody. Good morning. I have an advice at 10:30 in the during the coffee break. We will take another picture of the event. So be here. Well, it's a pleasure to me to introduce the last lecture of the regularity structures in the course. Thank you, Lorenzo.
Okay, so let's try to conclude again some discussion of the example and some discussion of the general theory. In a sense, I have explained you in a sufficiently detailed way the beginning of the theory, in particular this analytical structure with the two main theorems. Well, yes, so the reconstruction theorem and the Schauder estimates, which are certainly two of the most important tools. But then there is still a long way before the end of the story. And okay, today we just give an overview of that. So yesterday we were discussing this operator K bar on the light. Yes, thank you. On model distributions. Okay, I have corrected a few typos. Yeah. Okay, and then I wanted to make some comments because some of you asked me, and indeed, so so in the statement I said that you start from a model pi gamma, and then you apply this convolution operator, and it is natural, in fact, that so at least it is the case that your new model distribution will be associated to a new model. Okay, so in fact you are taking essentially convolution also with the model. Okay, so in particular the pi's will be the pi bar will be a family of convolutions with the pi that you had previously. Okay, that's not a problem. But in the application, then in fact, I wrote that kappa bar went from d gamma to d gamma plus beta with the same model. So someone noticed that, and indeed, so when you work on a problem like SPDE, you cook your model in such a way that essentially the pi bar gamma bar is at least a truncation of the pi bar gamma bar is already contained in your model at the start. Okay? And so therefore, indeed, this is a map which goes from this space to this space. So just for an example, think of the classical set of Hölder functions and therefore of the classical model. Okay, so first misprint. So this is not a plus, this should be a maps 2. Okay, so a 2 / 2. So here, what you're doing is you're going to a function which is C gamma, so it's Taylor polynomial finishes before gamma. to a function in gamma plus 2, so its Taylor polynomial finishes after gamma and before gamma plus 2. So here pi at the start is given by the standard monomials up to gamma, and pi bar gives the monomials up to gamma plus 2. So a truncation of pi bar, of course, is contained, in this case, is equal to pi. Okay? Well, so this allows indeed to build this map and the fixed point. And this tells you that the model will be built essentially in a recursive way. So let me give an example. So you start, so you study again this nice equation. So, okay, since you have psi, then you certainly want to have a symbol. Okay, so one of your indices in your index set, you want a symbol for psi. And then I didn't write that you will of course define pi x. Okay, again, you see. So pi x of dot of y will be psi of y. Remember, at the start, psi is a smooth function, so you don't need to worry about computing psi at the point. Okay, then you iterate a first time, so it means that you apply this construction and you build the new model pi bar gamma bar. So what happens is that you have to take a convolution with the object you already have, and then you get, so G convolution psi at y. Okay, but then you don't stop, you cannot stop there, because I told you, okay, we should keep track also the homogeneities. So this is the typical regularity of a white noise. So this is -1 minus kappa for d equal to 2. And then the homogeneity of this, so lollipop, should be this plus 2, so 2 minus 1 minus kappa, so 1 minus kappa, which is positive. Kappa is small, okay? Kappa is positive but small. Okay, so you want the pi x of the lollipop of y to be, say, bounded above by y minus x to the 1 minus kappa, and therefore you're more or less obliged to subtract this value at x. And okay, the construction tells you that because of that, so this is a zero order Taylor polynomial, okay, and then you have to add the zero order monomial, okay, and then you have lollipop and 1. So plus, of course, what you already had, which is the dot. So at the first iteration, this is the model that you obtain. In principle, if you go on like that, okay, since for reasons that I will discuss later, our global exponent, I already said it yesterday, is this 1 plus 2 kappa. If you apply again integration, 1 minus kappa plus 2 is way beyond the 1 plus 2 kappa, so that's not interesting for us. On the other hand, we had another very important symbol in the model, which was this one, which comes from a product. So again, products are the main source of difficulties, and also in the sense of the most interesting object. So in fact, again, integration only will never, okay, if you start from dot, you will never reach such a symbol with integration only. you add the symbol exactly because you want to write products. So because in your equation there's u times xi, so this represents xi, and this would be at least the beginning of an expansion of your solution u, okay, just in a generic way. But it's clear that in your space of model distributions, in order to represent this, the right-hand side, you want to consider some product between xi and this kind of object, which means that so you want to add also this this thing. I'm coming back to products later. So you see, this is recursive. You are applying to your symbols the operations which are relevant for your equation exactly in such a way that in the end your map acts on your space constructed with respect to that model. So now again, the homogeneity of this symbol is always there is an additive. So since this is a product, so this is the sum of the two homogeneities. So it's 1 minus kappa plus minus 1 minus kappa. So minus 1 minus kappa, so it's minus 2 kappa. So it's negative. Okay, and then you apply, if you apply integration to this one, this will become 2 minus 2 kappa, which is again larger than our global exponent 1 plus 2 kappa, so we ignore it. On the other hand, if we want to go to 1 plus 2 kappa, then we may have to include, we saw this yesterday in the computation of the remainder, that we have to include also these standard classical monomials. And then when you take the product, you also need the dot times the monomial, so you have to include this as well. So have we finished? We should have 8, I think, symbols altogether. So we have 1, 2, 3, then 0 is 4, the 2 standard monomials 6, and the 2 standard monomials multiplied by xi 8. So we have already a family which is now stable under all these operations, okay? Say modulo truncation when we go beyond the 1 plus 2 kappa. Okay, so every time that you have to study an equation for this with these techniques like 543, KPZ, whatever, so you have to first find the list of symbols which are in this notation actually represented by trees. Okay. Now the problem is that this is not always very simple. I told you already that sometimes you are in the hundreds of objects. Now there is one equation that we studied in a paper with Ivan Brunet, Martin, Franck Gabriel, and myself. So if you consider an equation like this, well, let's say, so it's something like that. Now here the dimension, this is parabolic, the dimension is 1, sorry, the space dimension is 1, and then you have time, which is an additional dimension. So this is KPZ type, but with a coefficient which is generic here, another coefficient which is generic here. So I don't exactly remember, but the symbols here are more than 50. Okay, so if you try to find them by hand, again, it's painful. yeah, okay. Just to tell you that there is this combinatorics. And by the way, the fact that you represent this by trees is natural because you have a recursive objects. Okay, so you know that trees have this nice structure that when you actually rooted trees, okay, this is important because you know what the last operation that you did in a sense is represented by the root. So there is time. There is how to say the iterations are in a precise order. Okay. So anyway, on the example, we saw the list of symbols. Now, again, I think we said this already yesterday, but it's really very important. So this recursive construction, if you start from Xi, gives you all the symbols, gives you all the pi's, okay? The only one which is outside this recursive construction is this one, so which is again the most important one. So the other ones follow, I mean, with their properties, okay? So you can build them, show that they have the correct analytical bounds and algebraic structure, etc., by general considerations, while this one is much more delicate. So Luca yesterday discussed this with you. So what one does is, now we start really working with the true random PDE. So we consider Xi equal to a white noise, and we take a convolution with some family of modifiers. So now Xi epsilon is, okay, here maybe you choose the modifiers which are symmetric. Okay, so maybe there is some small constraint of rho epsilon, but you can just think of Xi epsilon as a smooth function which will converge to Xi in the limit. So, and then this is a good definition, but we know that when epsilon goes to 0, this will not converge to anything because, okay, in fact, we know already that the mean, so if you take the expectation of this, this will diverge, while the rest of the distribution remains is convergent. So in a sense, this is something good plus a constant which diverges. So that's not what we hope for. Okay. So in fact, it turns out that if you define pi hat epsilon equal to pi epsilon for tau different from this symbol, and pi hat epsilon on this symbol equal to that, where, okay, so this was discussed yesterday by Luca. So then, indeed, we have convergence in probability to a distribution. And more generally, so the whole model converges almost surely to a model that I can call pi hat gamma hat, and I can call the renormalized model. I'll come back to this in a second. Okay. So, so there are many, I think, many interesting things to discuss about this. So let's say, and this is a general fact in this business of singular SPDEs. So we said at the start that, so the product U psi was ill-defined for, say, regularity reasons, okay? Okay, maybe I didn't repeat this, but Luca made it quite clear. So psi is 1 minus, so minus 1 minus kappa. U is at best 1 minus kappa. So the sum of the two exponents is minus 2 kappa, which is negative. So if you discuss with an analyst, okay, he won't be able to solve this equation if psi really is a distribution with that low regularity. And in fact, this is related again to this. So for again, this would, you can consider this as a product of two distributions, but it's the same. So in the limit, psi is -1 minus kappa. This is 1 minus kappa, and so the sum of the exponents is negative, and therefore, again, you don't have you don't have a continuous product which extends the pointwise product, okay, and which is continuous in the topologies. So C 1 minus kappa times C minus 1 minus kappa. Okay, so this does not converge in a simple way. Okay. Now, so there are several things that I wanted to say. So let's start from this one. So I mentioned that one of the key points is this continuity, okay? Namely, you define the model distribution as the fixed point of this map. And then, so this still depends on the underlying model, and this map is continuous, like for paths, etc. Okay. So here I was maybe a little bit sloppy. So I said that topology had to be made clear, but that we understood the topology as convergence, if you want, of every component pi ix in this space. Okay. Okay, more precisely, so if we speak of continuity, it's because the model is varying, but then we should specify where it varies. So, okay, what can change, what cannot change, okay? And in fact, so regularity structures, which I did not want to discuss until now, play this role, so they are giving some constraint, okay, a structure indeed, and the model can vary in a certain class, which depends on the regularity structure. So let's now discuss this. So in fact, according to what we saw above, maybe provocative definition would be so that the regularity structure is just the set of homogeneities, okay? So and the index set I. Okay. Okay, the point is that if you do that, then you have to impose some conditions on the model, but then it makes sense to include these conditions in the definition of the regularity structure, so that then the definition of the model is a bit shorter. But okay, you see, it's not much deeper than that. So okay, let's be slightly more how do you say, detailed, again in a reasonably simplified setting, okay? Because the definition Martin gave at the start was probably meant to cover very general situations, but in a setting like that, where you really have just a finite, we had the 8 symbols in our model. Okay, we don't need to think of infinite dimensional spaces, etc. So here we have a pair AG, where A is again the set of homogeneities, so it's a finite set of real numbers, full stop. And then, okay, G is a subgroup of the space of linear automorphisms of R to the I, okay, such that for all gamma in this, so it's a set of matrices, if you want, a group of matrices, such which have these 2 properties that were mentioned several times. So they are they have, so ones on the diagonal, and they have this triangular structure with respect to the homogeneity. Okay, so you can order the alphas by because they are real numbers, and then you have this this property. Okay. So I showed you during the second lecture that these properties are not strictly necessary, but they do allow at some point you have to introduce them. And actually, if you do this recursive construction that I mentioned, they are automatically enforced. So, okay, why not? And now, so the model becomes a model of a given regularity structure AG. And what is this? So it's a pair pi gamma such that so the pi's are a family of germs which have this homogeneity property uniformly over X in compact sets and psi bounded in a CR norm where R is fixed in this way. And so the gammas, I described them before just as elements of a matrix. Now I make this a little bit more precise. They belong to this group which has been fixed, and they have this flow condition and this kind of chain relation which connects them to the pi's. So in particular, I remember, so they have this triangular structure. Plus, you remember at some point we also discussed this nice analytical bound close to the diagonal. Okay. So by now you should feel relatively familiar with this definition. And then when we speak of continuity, so what comes next? No, I go back to the product. When you speak of continuity in this kind of statement, it means that given the equation, you have constructed the list of symbols with the list of homogeneities. So, and this has essentially fixed the regularity structure. Okay. So Martin is not here. So here I'll ask him later. So I actually always thought that I'm not completely sure why at the start, sorry, where is it? One needs to think of a subgroup of the linear automorphism of Ri. So I have a small idea, but I'm not sure that this is really so. So I think that one could just say G is the group of linear automorphisms such that you have this, and everything would be just as okay. Maybe at the end, if I remember, I will say why. Maybe I understand. But again, if you are in a infinite dimensional setting, etc., I guess that you do have to fix something at the start. Okay. Now, back to products. So, because this is really the crucial point. So again, singular SPDEs are singular when there is a product which is ill-defined. Okay, so that's the moment where the new say theory has to intervene. Now, in fact, in the example we had this computation. So we took this model distribution and we want to multiply it by dot. So again, in the aim of writing, say, a lift to the space of model distributions of the product between U and Xi. Okay, and then we used this product rule. Okay, so the dot times 1 is the dot times the lollipop is this, and the dot times the Xi is this. Okay, in fact, this is only a simple example. It's very simple because one model distribution is a bit complex, but the other one is very simple. It's just one symbol. So let's try to discuss this in a slightly more general setting. So first, very important message. So you don't necessarily want to write a product on all model, so on all pairs of model distribution. Okay, I said that at the beginning that you don't have necessarily a reasonable notion of square of the Dirac mass. Okay, you don't have necessarily a reasonable notion of square of the white noise, for example. Okay, so actually this exists in HIDA. How it's called, white noise analysis it's called, but okay, this is another story. It's not really relevant for what we are saying. So so you should not think that you will find the square of the dot or dot. Okay, so you want to multiply model distributions in such a way, okay, if you want, this is described here. So you want to put U1 and U2 in such a way that I is as a decomposition only for, okay, with certain symbols appearing. Okay, so you are also here, you don't have all the symbols of the model. Here you don't have all the symbols of the model. You have just the subsets in such a way that your set of symbols is stable under a certain product rule. Okay, so in this case, for example, you know that the dot times 1 is dot and this is this, and dot and this is this. So you see, it's just a small generalization of this phenomenon, okay? Because you want to have something which is well defined. So if you don't have dot square in your list of symbols, you will not take the product of two model distributions which both contain a non-zero coefficient for the dot. Okay, this will be forbidden. So this wouldn't have sense. And then you have gamma I, which is the exponent of both, so of each of them. And now, okay, so this is the theorem, which is again, okay, amazingly beautiful. So now we have to add some condition on the fact that gamma essentially leaves invariant the space. Okay, gamma should leave invariant the space of model distributions which are written in this way. Okay, and then it should be also compatible with the product rule. Okay, I refer to the paper by Martin for the details. But anyway, once you have fixed a good setting, then the result is the following. So you call alpha bar I the minimum of the homogeneities of each of the two sets. Okay, so this would be the first symbol if you have ordered by the homogeneity. So there is a unique bilinear extension of the product rule to a map. Now U1 to U2 goes to U1, U2 product. So where I'm repeating the structure. And now, okay, let's read this a bit in detail. So U1, U2 is the obvious formal multiplication of series, of sums, actually. So you take the sum over all J1 in A1, J2 in A2 of what? So you multiply J1, J2, which is in A because you have the product rule. And then you multiply the related coefficients. Okay? So, but you remember that when you are in a D gamma, you stop before gamma. So you truncate at gamma. Okay, so what is gamma here? That's one of the beautiful properties. So it's already written here, but let's think when you have, let me write. So when you have multiplication, so you have F in C gamma 1, so F1 in C gamma 1, F2 in C gamma 2, so these are standard Hölder spaces. So F1, F2 will be in which C, which is the gamma, such that F1, F2 belongs to C gamma. What? So take a C1 function times a C2 function. It's C. No. It's the minimum, exactly. So this is gamma 1. So the sum is the first guess, but if you think of it, in fact, this does not improve the regularity of the less regular one. So the regularity is that of the less regular one. Okay. So now, if you look at the formula which is there, you see something similar, but not quite. So there is a gamma 1 infimum gamma 2, but in fact yes, Milton. Yes. Yeah. Or maybe you can, but why if you don't really need that? So, yeah. Yes. Yeah. Yes. Yes. Yeah. Well, okay. In a way, this wants to be generic, okay, as generic as possible. Then, of course, if you have additional information, you can try something more sophisticated. But this is really nice, in particular because it's really the extension of that result to this setting, okay, and it turns out to be already efficient. So instead of gamma 1 inf gamma 2, you have to sum to gamma 1 so alpha bar 2, which is the minimum of the homogeneities of U2, and you have to sum to gamma 2 alpha bar 1, which is the minimum of the homogeneities of U1. So so these are okay. Okay, this should be negative. So I stated the thing in such a general way that now I wonder what happens if alpha bar 1, alpha bar 2 are positive. But in all the situations that we are considering, they are at most 0, because you always have at least 1 which is there, and then you may have something lower, which is what happens typically here. So this, in fact, will be less than the minimum between gamma 1 and gamma 2. And, okay, so the theorem, which is not particularly complicated, actually, tells you that, indeed, so this will be, again, a model distribution, which I remind you is not a trivial information. So it means that it has a strong, say, coherence between its coefficients with respect to the model. And so the homogeneity, sorry, no, the regularity is this one. Now, let us check this on the example of the equation. So, which is this one. So I'm considering this to be U1 and this to be U2. So U1 has regularity 1 plus 2 kappa, this because we decided it. I said it since the beginning that we wanted to work in this space of regularity. And alpha 1 is 0, okay? You see, so the lowest homogeneity which appears is 0. And then this one, okay, in fact, this one, since it's constant, it's the infinity, okay? There is no bound to its gamma, but its alpha is minus 1 minus kappa. And so you have to sum gamma 1, so 1 plus 2 kappa minus 1 minus kappa, which is then kappa. And then you have to sum 0 to plus infinity. So the infimum is clearly kappa. And so this is the result, so which I had written yesterday. So in the example, so this product belongs to d kappa. And actually, we chose 1 plus 2 kappa exactly in order to obtain this, to obtain something positive, and that's enough. It's not, you don't need it to be very, very large. It's enough that it is positive, so that you can apply all the theorems or reconstruction with unique reconstruction, etc. Okay, and now this is again a point, as I said yesterday, where when I first read the paper by Martin, I thought that he was making fun of me, because I told you this theorem is easy. So compared with other things which appear in the paper, there's nothing particularly fancy. But on the other hand, so we know that U1, U2, and the product are model distributions with positive regularity. So you can reconstruct them, and you can decide that the reconstruction of the product is a notion of product between U1 and U2. But U1 and U2 are distributions. So you are defining a product of distributions, which was, since the start of this whole business, the main problem. Okay? So this notion gives you a definition of a product of or at least certain distributions associated with a model. Okay, but where is the point? Why is it not true that Martin is making fun of me? So U1, U2, and U1, U2 are just collections of coefficients, and it is the reconstruction theorem which produces something non-trivial out of them. Okay, so this definition is actually, as I said, I don't know, easy. Okay, but the point is that you like, okay, in the example, this implicitly requires that you define this distribution. Okay, so the pi x of this non-trivial product has to be built in advance with all the properties which are required for a model to be a model. So in particular, you have to construct pi x of J1, J2 for all J1 in A1 and J2 in A2. And in general, this one is not correct, and 2 does not even make sense. So the left makes sense if you build the model, but the right, even if you build the model, these are really 2 distributions that you are not necessarily able to multiply. Okay, so it's very important that, so this product loses its connection with the pointwise multiplication. Okay, and yeah, at the same time. So you see, before all this theory, there were already results on SPDEs with this kind of problem that you had to multiply random distributions, etc. So when Martin arrived, so this had the success that you know. But why did what came before not have the same success? Okay, so it was because they contained notions of product which were not how can you say, not natural. They so here I take some risk because this has not been an easy discussion in the community. Okay, so because there are papers and which were published, and now after Martin published his theory, so those papers were somewhat I don't know, invalidated because they do something which is not the correct thing. They don't do the same as Martin does. Okay, so the author may disagree with me. It's legitimate, but this is a bit what is considered correct. So, so I'm saying that this notion of product is losing contact with the say physical, okay, pointwise multiplication, okay, but not in an arbitrary way. So I'm going to describe this now. And if you think, again, it's very important to keep a connection with the stochastic calculus because it's really relevant. So I said yesterday that if you define BS, DBS, well, this is the Ito integral, okay? So I said that maybe the Stratonovich integral is more reasonable because this is the rule that you apply for standard C1 trajectories, okay? And I said, well, minus t here seems rather unnatural. So what and this is a bit the same thing. So this kind of notion, maybe this is the physical definition of DBS. Indeed, the physicists prefer Stratonovich usually to, because it's more, yeah, why? Okay, sorry, why? Because if you regularize the Brownian motion and you write the integral from 0 to t of b epsilon s b dot epsilon s ds, okay, and you take the limit, so it's much more probable that you converge to Stratonovich than to Ito, okay? And for a physicist, so Brownian motion is an approximation of reality and not vice versa, okay? So so again, the problem of stability, you see, the same we discussed. So for a physicist, white noise, okay, has to be stable under some form of perturbation, and therefore it's more natural to think that this is the correct integral if it is the limit of this. But so we probabilists like to use martingales, and therefore we like this, and therefore we define this product, and then we integrate with this okay, additional constant. But then that's the same. So U1 star U2, even if we are okay, suppose that U1 and U2 are functions, we may want to define their product as something different from the multiplication product, but for reasons which are related to what we are doing, not just because we don't know what else to do. So okay, I'm going to try to show this again on the example. Yeah. Yes. Yes. I think so. Yes. So yeah, because if you see what is the t over 2, it is the constant which you need to center b squared t over 2. So you are centering, okay, and that's more or less what you're doing also on the model. So there is a centering operation, okay, because I said the mean is diverging, so you want to remove the mean, centering the distribution. Yeah, okay. Well, yes. This, yes, okay. at the same time, the model is a nonlinear object because you have the pi and the gamma, which are related by a quadratic relation. So just subtracting the mean does not necessarily preserve the structure of the model. So therefore it's a bit more complicated. But at least from the start, the idea is certainly this one. Okay, you see that it's a bit complicated, but yes. Yes, yes, exactly, yes. Well, okay. Wait a second. What? Yes, but because you're thinking now of the shuffle, is that what you have in mind? So is it the G which is here? Yeah. Well, okay. This morning, but I didn't have time to develop. In fact, I don't. In this sense, it's not exactly the same example. So, okay, maybe we discuss this later. Okay, it's interesting, but I did not manage to go to the end of the of the reasoning because I didn't have time. Okay, so again, very important message. So once you have constructed your model, so this defines a notion of product of your distributions, not any distributions, but the ones which are produced by your model distributions. And when you change the model, you change the product. Okay, in this sense, this is really, again, related to Ito Stratonovich, because you know that when you study an integral, okay, so the integral from 0 to t of Hs Stratonovich dBs, okay, so there is a rule to go from Stratonovich to Ito. Okay, so Stratonovich is Ito plus 1/2 quadratic variation between the two processes. Okay, and in case H is also semi-mapping, and this is telling you that if you choose one situation or the other, so the product is not the same, not only for B, but then for a general class of objects. Okay, and then in the equation this appears as well. And again, let's see this on the example. Okay. So we go back to this renormalized model. Why is there a small hand? With this constant. Indeed, in this case, we have lost the pointwise multiplication. Okay, so this constant here. So this was the true pointwise multiplication, but we are removing a constant, so it's not correct anymore. Okay. Now, indeed, so this is called the renormalization step. So notice that here we have a constant C, which may be also more general at this stage, which acts on the model. So I said additively in the sense that the action is really the action of the group R with the multiplication on the model. Multiplication with addition. Okay. Okay. More generally, one has a group, which is called the renormalization group, with an action of the space of models over a fixed regularity structure. So let's say in situations like this one we are considering, the group should possibly be finite dimensional. So if everything is translation invariant, then it should be fine. Okay? But this is the famous algebraic part which scares people, and which I don't want to now explain in detail. Let's just say what is the phenomenon. Okay, what is the general picture? Now, I remind you, we want to find u as the fixed point of this map. Now let's go back. So this I copied and pasted from yesterday, but now we use the renormalized model, and we check what happens in our construction. So we lift the equation to the space, to this space. Okay, so we start from V there, and then V has this decomposition. Sorry, no, okay. This is actually a subspace of D1 plus 2 kappa, okay? I start with V, so it would be more correct that to define a subspace which this particular structure, and in this setting, so the coefficient of 1 is the reconstruction of, and this comma is a typo. Okay, then we write again this product. We already discussed this, and we discussed the fact that, so let's call it W. So dot times alpha plus beta V belongs to D kappa of the same model. Okay, this is general. For the moment, we have not used the form of the renormalized model. So now let us reconstruct W. So again, W, don't forget, is this, is dot times alpha plus beta V. So in this case, since all elements of the model are continuous functions, we still have this formula, which means that we just apply pi epsilon x. Sorry, I told you that there would be a number of typos. So pi epsilon x to the model distribution, and then we compute for y equal to x. So this is what you obtain. Now you immediately notice that this cancels because here, so if you remember, this is psi of y minus x. So for y equal to x, the y minus x cancels. So this does not appear in the second line. Here I'm writing what this means. So by what we wrote before, this is G convolution psi at x minus G convolution psi at x times psi at x, sorry, minus constant. Okay, now again, this cancels, but the constant does not cancel. Okay, and so we are left with this expression. Now, here I did not finish to rephrase my sentence. So now I have to apply the convolution operator, and this is the part which you did not want to listen to, so you don't know the why, but this is the outcome. So it turns out that here, so that's why I computed the reconstruction. So the coefficient which multiplies 1 is G convolution with the reconstruction of W, which is correct because this is what you expect then if you reconstruct this model distribution, plus this, important, this was already the case in the general situation, plus this, okay. This will play no role in the next slide, so I did not bother to compute the coefficient. So these two terms are the important ones. Why so? Because if I go, yes, please. Yeah, exact. So C epsilon is the correction term. Yeah, so this is what would be T over 2 for eta. So, okay, let's repeat this. It's a good point. So you start from, no, but let's say this. So when pi epsilon is equal to this without the C epsilon, okay? So without the hat, you don't have the constant, and then it's multiplicative. So it's the standard rule of multiplication. Okay, and it's like Stratonovich. Yeah, and then when I put the hat, I put a correction. It's a minus C epsilon, which is like a minus T over 2. Okay, and the aim is exactly to have a zero mean for this object. Okay, and okay, exactly, and then this corrector, it's like what I wrote here. Maybe okay, you can write it in the opposite maybe way. So so maybe it would be more correct to write it like that. So more. So we started from Stratonovich and then we built Ito in this way. Yeah, I can't hear. Okay, can you? Yeah, yeah. But okay, so this is the correction term. Okay. Yeah. Yes. Exactly. And yeah. Okay. Now there is just a final ingredient, because here we don't know what what this coefficient is, but in fact we had already seen this. If you have a fixed point, so this is, yeah, okay, sorry, I have to go back. You see, V, this is the coefficient of the lollipop, okay? So if you have a fixed point, then the coefficient of the lollipop has to be equal to this, okay? And so, but V actually here, this V was the reconstruction. So the reconstruction is U hat epsilon. So this is telling you what this coefficient has to be in the case of the fixed point. It has to be equal to alpha plus beta U hat epsilon. And so you put alpha plus beta U hat epsilon instead of that coefficient, you get this. And then in this particular case, you can rewrite just things like that. Okay. Okay, it's just so again, I already said yesterday that the lift to the model distributions had an effect also on these coefficients. This did not change the equation, but so you see here that so you see here in the end that U hat epsilon is the reconstruction of this, and then you obtain what is called a renormalized equation for the a renormalized equation. Okay, so your equation at the start had no C epsilon, but then you add this C epsilon, and this is the equation whose solution has a chance to converge when epsilon goes to 0. So why does it converge with the information we have until now? So we have not proved it, but so no, yes, maybe Luca essentially proved that that renormalized model converges to a model. Okay, so in this case we know, and you have the continuity result, which I stated at some point. This Okay, so since this map is continuous, and since now we have a model which is converging, then u hat epsilon converges to a distribution. Okay, so what is lost is the equation in the limit. So this is maybe a bit troubling, but you cannot write that. So call it u hat. U hat of x is not equal to g convolution anything that you can describe. Okay, so because so this is getting lost in the limit. What is not getting lost is the fixed point, is this. So this remains perfectly defined. Okay, so when the renormalized model converges to the, say, limit model, the model the space of model distributions is still well defined, and all the analytical tools are still well defined. So the map k bar, etc., and the fixed point are still perfectly defined. It's when you reconstruct that you are not able anymore to recover this. Okay. Let's be. Maybe this is not without interest. So why? Because you don't have this formula anymore. Okay. So in the limit, the models is not made of continuous functions anymore, and so what you get on the right will be G convolution indeed. Well, the reconstruction of alpha plus beta u capital U times dot. So this is okay. This is well defined, but it's not more a function of an explicit function of U. Okay, you have lost this functional dependence with respect to U. Okay, so this is a bit maybe delicate, but again, anyway, it is very important to so you don't just have convergence. So you have a way of, say, characterizing your limit as the reconstruction of this model distribution, which is the unique fixed point of a well-defined problem, etc. So there is one thing which is very interesting here again, and it's again about products. So the fact that you have modified your products and therefore your equation. Okay, so you could tell me, this is again something I also thought at the beginning. Well, you have modified the problem. You were not able to solve the equation, and then you change the equation, you're able to solve it now. So is that legal? So is that really the solution of the problem? Okay. So one, again, maybe we could have a look at SDEs, because again, so here the situation is less dramatic in the sense that the Stratonovich is well defined. So in that setting, the analog of Stratonovich fails to converge, so it's clear that we have to do something. Okay, but for SDs, Stratonovich is well defined. So why should we not consider this as a, well, the point is that, again, first, in this setting, the integral of BS dBs, we said it several times, is not uniquely determined. So in any case, you have the choice, which one you prefer. Okay. So this one gives martingales. This one gives a nicer behavior with respect to, for example, to calculus. Okay. So by the way, you will remember that phi of bt is integral from 0 to t of phi prime bs Stratonovich dbs. Okay, so you don't have the Ito correction, exactly because the Ito correction is this other term which appears. So if you write the Stratonovich integral as an Ito integral, you get the Ito correction. Otherwise, you have this, which looks like the standard chain rule. Okay, so that's also a reason why the physicists prefer Stratonovich. So if you want this, you will use Stratonovich. If you want to work on manifolds, Stratonovich is well defined exactly for this reason, but Ito is not well defined for Brownian motions with values in a manifold. So again, you have the choice. Another reply could be that in this business of random distributions, why should u psi, so u times psi, be the limit when epsilon goes to 0, okay, of u convolution rho epsilon times psi convolution rho epsilon. So who said that this should be true? Okay, so this is our bias, okay, because we like pointwise multiplication and we would like this to be correct. But in this world of random distributions, again, as for Brownian motion, the rules may be different from what our intuition suggests. Okay, and then there is maybe a deeper reason, which comes from also what I read on quantum field theory. So the fact that also there, this renormalization actually was defined in that context. No, actually, okay, renormalization is even older. So I try to, I tell you because anyway, I have nothing to lose. But so there is a phenomenon which is the following. So if you have a ball, something heavy, you want to measure its weight, and but this ball is in water, okay? So there is a phenomenon that inside the water, so the effective mass of this ball is different from what you expect. So I should have prepared this. I'm now unable to explain you what this means, but it gives the following principle, which in QFT is very important, that the physical parameters of the problem have to be deduced from experiments. Okay, you cannot decide in advance what will be the mass thing, and okay, no, this what I'm saying is probably true, but I can't explain it properly. So let's say that there are reasons which come from QFT, which impose something which is called renormalization, and this traduced in this, so translated in this setting, gives exactly this strange additional terms which appear in the equations. Okay, so for example, 543, which has been discussed, as exactly the additional terms in physics literature that Martin and AJ discussed. Okay, I may have prepared this better, but okay, it's already a miracle that I arrived at the end of this story. So again, the renormalization means a transformation, a modification of the products, essentially. Okay, and it's not cheating; it's choosing the correct products. Okay, for the problem at hand. So in this setting, the product between u and psi is not correct if you don't put the C epsilon. Okay, and again, it's like the correction, the Ito-Stratonovich correction. If the good problem is the Ito integral, then you have to put the corrections. Otherwise, it's false. Because you don't go to the correct limit. So again, in this theory, what is very beautiful is that you do not need to control the product between u epsilon and psi epsilon, and that's better because u epsilon is unknown. It's the solution to an equation, but you don't control it explicitly. What you control is the model. So the symbol which is responsible for all this is this one. We said it okay many times. So once you have constructed the pi x on this symbol, that's responsible then for the correct interpretation of the product between the u epsilon and psi epsilon. Okay, so whatever u epsilon is. Okay, so that's the power of the theory. And okay, there is a last. There would be a last chapter, would be the convergence of the renormalized model. Well, this would require another series of lectures. There is a paper by AJ and Martin. There may be, so there is another recent paper by Marcus, who is here with Felix Sotto, Pablo Linares, and Tsatsulis. I don't remember the name. Thanks. And so they have another approach to maybe a less general problem of convergence of renormalized models. So Martin tells me that there will be soon another paper on this. So it's a very interesting but very difficult problem. It's really probabilistic. So unfortunately, in these lectures, there has been relatively little probability. But at the same time, some connection with the stochastic analysis has been discussed. And it's impossible, I think, to understand the theory without the material that we have tried to see together. Okay, so, well, this is the end of a rather long story. So it was 2 years ago when Dirk contacted me. Then the school was postponed by a year, which allowed me and Francesco and Luca to make progress on the Schauder estimates. And I am a bit tired now, but I'm very happy. Thank you for the interactions, which have been very nice. And see you next time.
Well, are there any other question or comment? Okay.
Well, yeah, just first a comment. If I want to convince at least a probabilist that the renormalization is okay, I always say that already at the level of the central limit theorem, one has to do that, no? Because if your random variables happen to have means different from 0, you already have to take out a very big constant, no, to make things converge.
Yes, of course. Yeah.
And also there is a renormalization group in a sense, because if you subtract the constant minus, let's say, what you have to subtract, right? Square root of n the mean minus a number a, you end up with
another variable.
Well, another variable. So, I mean, in a sense, for probabilists, all this should be difficult but natural, no?
Yeah.
So, something I never quite understood very well is that how this, as at the end of the day, models are non-linear, right?
The models, yes, are nonlinear functions of the noise. Yes.
Yeah, and but at the end of the day, you have a continuous theory of solutions,
Yes.
and that's a little bit strange in the sense that you're always changing topologies because you're changing models and you're changing everything. And at the end of the day, everything is continuous.
Yeah, but that's a really Terry Lyons idea. So just in a more complicated setting, but it's the same. Also, the rough path is a nonlinear function of B dot. So if you consider the white noise, right, or B also. But if you add this nonlinear functional, if you control it, then you control many stochastic integrals and in particular the solution to the PSD. So probably that's easier perhaps to understand, and then by analogy.
Okay. Well, anyways, thank you for your course. I hope all students have enjoyed at least part of it, because I understand it's a very dense material. Well, thank you.
Thank you.
Any other question, comments? Okay, in the name of the organizer, we thank Lorenzo. We all enjoy your course and your lectures. Thank you very much.
Thank you.
So now we will take another picture of the event during the coffee break session.
Hello? Sorry, there was some kind of lack of communication, but Maria Aurora Vares will be on the afternoon. Now there will be some exercise, Young Mills theory exercise with Harpy. Sorry, I don't know if I'm saying the name right. Okay, I don't know. You have maybe some PowerPoint slides? Do you have the PDF here? Okay, I don't have the slides. Do you have it in your mail or something like that?
Maybe a question. Does everyone have a tablet or something? I sent the exercise around, but it looks like we can't manage to get them. Otherwise, I can try to yeah, otherwise I think it's fine without slides as well. Hi everyone. So I will continue with the exercises. So I sent around an exercise sheet at some point in the WhatsApp group, in case you have it in front of you. There were some typos in that as well, so I might send a version with less typos like this afternoon at some point and point out maybe the little errors. So the first exercise is about the Gaussian free field. So and for technical reasons, it's kind of nice to work with a massive Gaussian free field. So what is the massive Gaussian free field? So we are working on the torus. And then the massive Gaussian free field is a centered Gaussian field. So and since it's a centered Gaussian field, it suffices to prescribe its covariance. So, so what formally we write is that h of x, h of y, that this covariance is the Green's function x comma y. And since we're working with the massive Gaussian free field, it's g is the Green's function of the differential operator Laplace minus, and we fix mass to be 1 of this operator. So now kind of depending on what convention one uses for the Green's function, so the covariance has to be a positive definite guy. So I mean, if we just want to take the inverse, it would be the minus this guy. So, but that's kind of a question of convention. So what should one think of here? So the Gaussian free field is really the natural analog of a Brownian motion if the underlying space is higher dimensional. So, now it's up. Thank you. So, okay, and and this is, I mean, this is clearly just a formal definition, since g of x would be infinity, and that clearly doesn't make sense. So one has to make this somehow rigorous, and one thing that's very common, at least in this community, is to say it's a random distribution, and we just test against test functions here. But something that will turn out to be quite useful is actually we can see it as a random field over a set of measures. So what we can define is M, let's say mg, to be signed measures, signed Borel measures, mu such that the following expression is finite. So we take g, x, y, and then we take d mu x, d mu y, and then we take absolute values since we want to work with positive guys. And what we enforce is that this is finite. So now this makes sense as a random field over this space, but so far it's just a random field. And the first exercise is kind of to see that actually there exists a modification of this, which is a random distribution. So, but before I start with this, so it's kind of useful. I mean, since we're working on the torus, one nice thing that we have is that we can actually take explicit Fourier transforms. So we can look at, we can first kind of understand this guy slightly better. So for that, we take a Fourier basis, so a k, or k is now in ZD, and explicitly a k is given by the exponential of 4 pi squared k scalar, let's say at z, k scalar product z. So, and then also let's introduce the notation. So we want to take the Fourier transform of functions that we test things against. So what is useful is to kind of know how the operator acts on AK. And okay, this is not a difficult calculation. So what we get is that this is minus 4, there shouldn't be a square here, and I think it should be a 2 here. And then we get a 4 pi squared k squared plus 1 ek. So, okay, and then let me introduce a little bit more notation. So the Fourier transform of Schwarz function f is given by f of k. That's the scalar product with this ek function. So f comma ek, which is the integral over the torus of fz and then ek bar z. Now we have this expression, so we can actually calculate the inverse of this differential operator explicitly, since, as we see, kind of this Fourier basis diagonalizes it. So, so let me actually quickly do the calculation, since it's quite short. So what we can do is, okay, the Laplacian minus 1 applied to some function f. We can just decompose f. So we get a sum over k and fk ek. And now we know how this acts. And actually, let's just apply the inverse operator directly. I mean, and what we find is that this gives us minus the sum of 1 over, okay, since we are inverting the eigenvalues, so here you get the 4 pi squared k squared plus 1 down here, and so then we get a ek f hat k. So, and if we recall what this thing is, what this integral is, we actually see that this can be written as a convolution. So this is the same as we take the integral of, well, the same factor 4 pi squared k squared plus 1, and then here we have ek, and there's one minus hanging around, ek of So here we're integrating. So let's say z minus z bar, f of z bar, dz bar. So, and let me put a z here and then a z here. So I mean, this is very kind of basic things, but one thing that's kind of nice. So I mean, the arguments also adapt to general domains, not necessarily the torus, but then you have to have some knowledge how to diagonalize the Laplacian, and kind of on the torus, it's very nice since it's very explicit and simple. Okay, so this guy we call g of z bar. And that's this Green's function here. Okay, so the first claim that we want to check is that this is actually a random distribution. And for that, let me go here. So what we took as non-formal definition is, so H is a field over mg, right? So we have these measures mu, and the Gaussian free field is mu, where mu is in this set of measures. So what we want to do formally, we want to see that there is a version of this guy. So we kind of see that Fourier transforms are nice, so we can attempt to just formally find out what the Fourier transform of H would be. So we define H of k to be given by so we H of, and now there's kind of the natural thing to do is kind of to take a minus. So what if H were a function, what would that be? That would just be the scalar product of, or kind of testing against EK, and that now that's now the same as H, and now here we put a measure, and since we have a complex conjugation here, it's kind of E minus K or EZ, so that measure. So, and that makes sense. That's a signed complex valued measure, and it satisfies this property clearly. So that's how, okay, so we have defined a random variable that we formally write like this, and one thing that we might want to do is kind of to see what law these things have. So certainly if we vary k over zd, these are all Gaussian, they're all centered by definition. So what we want to calculate is the expected value of h hat k, h hat, let's say, m. Okay, and so for that, we can go back here, and what we see is that, okay, we put in f is one of the Fourier modes, so that enforces that in this sum, which I forgot to write, the only Fourier mode that survives is the same one. So what we get is exactly that expression, so it's 4 pi, let's say, k squared plus 1, and in here what's enforced is that m is equal to k. So okay, so what we know is that kind of the Fourier modes are independent, and okay, one thing, so we are working with a real valued Gaussian free field, so that imposes the condition that h hat of k is the same as h, okay, minus k is the same as h of hat of k complex conjugated. So I mean, that's just because we're working with a real valued Gaussian free field. At this point, that doesn't play a big role. Okay, but so what we know that this is the covariance. So in particular, if we define xk to be h hat k times the square root of this expression, so 4 pi squared k squared plus 1, then these are IID standard normals. So, okay, now we want to see the Gaussian free field as a random distribution, we have kind of tested it against the countable set. And so a natural ansatz would be now to say, okay, what should it be? The Gaussian free field should be given, if we want to interpret it as a distribution, by kind of h hat k, then ek, which is the same as kind of by definition the sum, okay, a sum over k of x k divided by this expression 4 pi squared k squared plus 1 ek. So we have actually a random Fourier series, and okay, now one can try to see almost true properties of this random Fourier series, but in particular we have found the random distribution. So we can take, I mean, we can take the modification that kind of, that on smooth test functions agrees with testing that guy against smooth test functions, since Fourier modes are dense. Okay, so we know it is a random distribution, so the other thing we can do is kind of to look how it behaved again if we test against localizing test functions and we want to apply kind of a Kolmogorov type criterion. So what we want to calculate is if we take this random distribution that we've defined here, we test it against some localizing test function. So we want to calculate this expression where it's the same notation as usually. So this is the same as lambda of 1 lambda to the v dot lambda. So it's kind of a Dirac scaling as we let lambda get small. But actually, we have quite a lot of information by now already. So one way we could do it is actually we take the Fourier transform on both sides. So we get, this is the same as the expected value of, well, just putting a hat here and a hat here. So, and what we know is that, so the scaling that preserves L1 on the real space is the scaling that preserves the L infinity norm on the Fourier side. So that fact translates into this kind of an expression. So that's lambda dot. And the scalings are in the opposite directions. Okay, so what we want to calculate is kind of testing h hat against phi lambda. Okay, now phi should be, so there should be a hat here. So let's call that psi lambda dot. And taking the square of this. So that's what we want to calculate. So as the next step, we want to use the fact that we have a very explicit expression for this. So so before we take the square, so this guy without the square, that's simply given by the sum over k of, well, this okay, we have this, okay, x k's, right, divided by 4 pi squared k squared plus 1, square root of this expression. Then we had the ek's, which, okay, yeah. Okay, so chi is the Fourier transform of phi. So this expression, and then we have here explicit. So this is, I mean, so this, so what we, okay, so here we get the chi of, the scalar product is really the sum here, and here we have this lambda hanging around, and we get this k. So that's the guy without the, taking the square. But now we know that these guys are IID, so the full expression becomes the sum over k. So first we would have a sum over k and L, let's say, two indices, but since we square a sum and all the components are independent and centered, this cancels and simply gives us square root of 4 pi k squared. So no square roots, okay, plus 1. And then these have to agree, so that just contributes a 1. And then here we get chi squared lambda k. Okay, so now this guy was a localizing test functions with good properties. So now this is of order. Okay, so this sum, if we assume that chi was compactly supported, is the sum over k's that are smaller or more or less smaller than 1 over lambda. And now here we just have this 4 pi squared k squared plus 1. And now, depending on the dimension, this, I mean, generally this, so in dimension 2, this is kind of barely not summable. In dimension 3, it's kind of a bit worse, but this turns out to be of order lambda to the minus dimension plus 2 plus and then minus epsilon. And this minus epsilon is because in dimension 2, this is kind of a logarithm, and it's the logarithm is barely not bounded. So, okay, so we have this, and kind of, I guess, in the lecture, we've also at least heard of kind of Kolmogorov type criterions. And I mean, okay, so what we know that this thing is Gaussian, so we get the same bound modulo changing this constant if we take any power p here. And so, and Kolmogorov criterions, they usually come, I mean, they usually come from the fact that you have a good understanding of your space. So one, for example, good functions to plug in here would be, yeah, question. Yes, but H hat, we have the explicit formula, right? We defined, okay, kind of, we defined H hat to, I mean, H hat was defined here, and X was defined such, I mean, by this expression. So we had this formula where these are IID standard normals. I mean, this thing is H hat. Or where are you? Or the H hat disappears because we then get the standard normal. And then this is a chi, so this maybe was a bad notation. Maybe let me take another symbol here. Okay, maybe now it's a bit better. So here now the x's appear. So because the Gaussian free field is really this superposition of Fourier modes with these random coefficients. Okay, so okay, one thing I want to point out is that, okay, so this sum, there's kind of a lot of cancellations. It's like the fact that 1 over n is not summable, but if you put random variables up there, it's almost surely summable. So this thing will converge if we test against many different things. But to be a random distribution of certain regularity, we don't just enforce that, but we enforce it to converge at the same time for many different things with explicit almost sure bounds. So, and then, yeah, so to get this kind of criterion, so it's very useful to either test against wavelets or to test against Littlewood-Paley blocks, because they are very efficient at approximating any, so if we do that approximation, that's very efficient to get to any test function. So the error you make by exchanging kind of supremum and expected value is small, because these are efficient ways to explore kind of your function space. It's kind of like for the Kolmogorov criterion for Brownian motion. So what you do is you approximate any interval very efficiently by using dyadic approximations. So it's the same thing, but I mean a bit more complicated. But you want to get a Kolmogorov type criterion, you always want to be efficient in getting to any interval in your space. Okay. And so now the next thing that I want to quickly discuss is the fact that the Gaussian free field is stationary under the stochastic heat equation. So that thing there, and there is a typo, so there should be a square root of 2 in front of the white noise. So now we have H, we sample H, it's a Gaussian free field with mass 1, and we look at the stochastic heat equation, we let that random distribution evolve under this equation, and the claim is that at any time it will still be a Gaussian free field. So let me clean the blackboard. So, okay, maybe. Okay, so what are we looking at? So let U be the solution of the following equation of dtu minus equals Laplace U minus U plus space-time white noise, and U0, U at time 0 is H GFF, and it's independent of the white noise. Okay, but before we even care about this, so one thing that we've noticed, and is here is very useful, is to kind of take the Fourier transform. So what we do is we know how this operator looks if we take the Fourier transform here in space. Here nothing changes, and the thing that you can check very easily is that if we have this random Schwarz distribution, we take the Fourier transform. So now let me write the Fourier modes here. These are IID time white noises, so white noise. And IID with complex, IID complex. And then we have again the thing that we wanted to be real valued. So psi k is complex conjugated to be the same as psi minus k. So, okay, this is nothing much happened. This you again check by just looking at the covariance of this guy. Now we want to check that this claim actually holds. We know what the Fourier transform of the Gaussian free field looks like. So what we want to do is actually, okay, take the Fourier transform of the equation. So we get that dt u hat is the same as minus k to 4 pi squared k squared plus 1 u hat plus, okay, and let me put k's here, k, and psi k. So, and this type of a SPE, we know what the solution looks like. So, okay, the solution is a sum. So UK will hat. Okay, first it is the solution to the guy without any noise. So that's then given by U0. Okay, hat, and at time 0. So let me, yeah, so k, okay. So we have a k and the time, right? K is kind of the Fourier mode. So, and then here we get that this is e to the minus 4 pi squared k squared plus 1 times, okay, and this we evaluate at time t, so we get a time t here. And then the other term is given by Duhamel's formula, which is the integral from, okay, we're starting at 0 to time, let's say, okay, we have small t here, so then we get the same guy, so the flow under this differential operator, so minus 4 pi squared k squared plus 1, and now we get t minus s d psi, and then we have k s. So we have this explicit formula. So one thing that I maybe want to do here is already take the square root of 2, put here a square root of 2, and then that's the typo on the thing, so things work out. So, and what we want to show is that this guy is still a Gaussian free field if this starting guy was a Gaussian free field. So, what do we want to do? So what it suffices to show, so what it suffices now to show is actually that this guy, so let me call, so that this guy is in law the same as the integral from 0 to t of square root of 2 times exactly that expression. So 4 pi squared k squared plus 1 t minus s. And then I get d psi. So, this should be from minus infinity to 0. Sorry. So, I mean, since if we have this expression from minus infinity to times 0, that thing is clearly stationary. So, if if the first guy satisfies this property, the whole thing can be written as an integral from minus infinity to time t, and that has clearly the same law independent of t, because it's the same integral modulo of time shift. So far, everyone happy? Okay, and I mean, this is not difficult to do, so it's again something Gaussian, so it suffices to know its covariance since it's clearly centered. So, and then since the noises are IID, clearly for different k's, this expression is independent. And so it suffices now to calculate, let's call this left-hand side of k. So this guy is left-hand side k. Okay, and we take the square of this guy and we want to know what this is. And okay, so this is now, okay, the square root of 2 goes away and we get a factor 2. Then we get an integral e to the minus that expression squared, so 2 times 4 pi k squared, 4 pi squared k squared plus 1, and then we get a ds from the minus infinity to time 0. So, I mean, what we just use here is that the covariance of white noise is a Dirac. So, I mean, this would be dB, maybe d psi is. I don't think it's irritating, but it's multiplying by the derivative of Brownian motion. Okay, and this thing is very explicit, so we are actually, okay, so here there should be an expression t minus s. So what this is, so we can take out this t term since t does not appear in the integral. So let's keep the 2, then we get the e to the minus 2, 4 pi squared k squared plus 1t. And then we get the integral that's left over from minus infinity to 0, e to the minus 2 times 4 pi squared k squared plus 1 t, okay, no t left, so minus s ds. I mean, we are already very happy, are we? Yes, so, okay, and so this guy squared would be exactly that guy modulo this factor 2, but this factor 2 we will take care of now. So the 2, let's put the 2 still here. So that's okay, so that guy is, and this guy squared is exactly that guy. So we want to see actually that this second term is actually a Gaussian free field, or kind of has the right covariance. So let me clean the blackboard again a bit. Okay, so, and this integral, so it's from minus infinity to 0, but of minus s. So what we can certainly do is go from 0 to infinity, and we kill this minus here. Then this guy is exactly given by 1 over 2, so minus 1 over 4 pi squared k squared plus 1. And evaluated at infinity, and then, okay, so this is exactly the expression, what this integral gives us, which is very nice since this kills us this factor 2. That's also where the square root of 2 typo came from, and that's exactly the weight on the Fourier mode that we had for the Gaussian free field. So, okay, so we have shown this. Maybe one comment, so one does not need to use Fourier analysis if we had another, I mean, if we just can decompose the Laplacian eigenvalues, then this calculation goes through, right? I mean, it's not, but, okay, so that was about the Gaussian free field. So let me check where I put the thing to turn the pages. So let's see. Okay, so now let's talk a little bit about these spaces of distributional one forms. Are there any questions? So one thing that we already saw in a definition, so we had this definition of the Gaussian free field, which is still there as this centered Gaussian field over measures. And one thing that we see is that we can put the kind of a Dirac mass along a line in there. So we can, since the Green's function is somehow a logarithm, we can integrate the logarithm over lines. And that's kind of the reason that we can integrate the Gaussian free field over lines, by definition, essentially. So, okay, but first maybe a little bit of recap. So we can work. So yesterday in the lecture we saw that, okay, if we have a curve gamma, then it's very natural to kind of associate to it the volume of the associated triangle at 3 points. So let's recall that. So we start with a curve from, let's say, R to R2. So then we define P of, let's say, T S U T to be the triangle. Yes, to be the triangle that's that's obtained by kind of taking gamma S, gamma U, gamma T to be this oriented triangle. And what we want to look at is the volume of this guy. So let me change the. So So we want to look at this volume. And okay, so now we can vary kind of what the regularity of gamma is, and the first claim would be along the lines that if gamma is in C1 beta, then PSUT is of order T minus S 1 plus beta. Okay, and that's not difficult to see. So what do we know? So we know that the curve gamma is differentiable. So we have a derivative. So we have a linear approximation. So let's say this will be gamma of S. Okay, and now gamma of T and gamma, and this is the vector would be gamma prime of S. Gamma of T would not times T minus S. This is this vector, but gamma of at time T will not be here, but we will make an error, and the error will be of order T minus S to the beta, right? Because that's Taylor's theorem. It says that if we approximate a C1 beta function, well, we have a linear approximation and we make an error of order beta. In the target point. So, I mean, and that kind of, okay, so we don't quite have a triangle, so the target point will be somewhere like this, somewhere in this ball, and then any point in between on the curve would also lie in some ball, and so now from this picture you can convince yourself that certainly it will be dominated by this times this base length. Since if the first point lies in this ball and around any other point you make a ball of the same size, if you take any 3 points, they're certainly in a square of that, let's say twice that size. So you get a bound of this order. Okay, and then now what is very useful and also was alluded to in the lecture is that it's nice to have a parameterization invariant version. So what we first define is, so gamma of ST, this we define to be given by the supremum over U in the interval ST, and we take the supremum of exactly that volume to 1 to the power 1/2. So what we now know is that if we are working with a C1 beta function, this will be of order 1 plus T minus S1 plus beta over 2. And that's kind of already where the next typo is. So that exponent there is not quite correct. It should be a -1. Okay, so, and now the next claim is to, so we introduce this parameterization invariant distance on this gamma. So we define this to be the supremum over partitions. And now we sum exactly this guy. So S comma U should be in that partition. And here we put gamma ST to the power alpha. Okay, and now there's kind of this 1/2 that got. Ah, yes. Thank you. Thanks. Okay, and now, okay, so for this expression to be finite, we know that this, so we have a bound on this expression, which is of this order. So what we find, so So for gamma alpha to be finite, we need that these increments or this exponent satisfies alpha times 1 plus beta over 2, and this should be bigger or equal to 1. And if that condition is satisfied, one gets, if that condition is satisfied, we are certainly in this case, so then one gets the statement with the corrected exponent if one does the algebra. Okay, so now let me come to the more interesting part. So one reason to introduce all these things is kind of, since, okay, so maybe a quick recap. So in the lecture, we introduced kind of these distributional one forms, and they were defined first on oriented line segments. And the point is if our space is regular enough and we have an appropriate norm on those, so we introduced this omega alpha, and if our space is nice enough, then one can take an approximation of our curve by line segments, and then this construction becomes continuous. So one has this pairing, and again, this exponent is wrong because of the reason above, but one has a pairing for the appropriate exponents. So, okay, now also one thing that exists is kind of this, there's a kind of Kolmogorov type criterion that tells us if we are given a random field over line segments, let's say, then, and that field satisfies these two properties, that then for a slightly worse alpha, one gets that one, there's a modification of that random field which lives in our C alpha, omega alpha space, and that it also satisfies a certain bound. So now we want to define that for the Gaussian free field, and we already know that we can test the Gaussian free field against the Haar measure on lines, not the Haar, Hausdorff measure on lines. So we are actually kind of in a good shape. But one thing that we notice, which is kind of important, okay, if we start with a smooth function, x, and we want to turn it into a one form and integrate it parametrization invariantly, so one uses one forms. So, but kind of the space of one forms is two-dimensional. So we would have something like dx2, and that's really so a function we can integrate on lines, but the thing about one forms is that they also have a sign. So we have kind of an assignment that if we integrate this thing, it's kind of minus integrating this thing, and the same if we integrate up or down, and that forces one to kind of look at these type of expressions. And especially if we want to lift the Gaussian free field, what we would like is that it's rotation invariant. And if we want it to be rotation invariant, I mean, we cannot just take a one-dimensional guy formally. We have to really take two. So what we do is we define big H formally to be H1 dx1, H2 dx2, where these are the standard one forms. This is so far formal. If we had smooth functions, we would be done at this point, but we want to give a rigorous definition. So we start with a line segment, L, which was denoted by xv. And now we want to plug that in. And so what we write is we write HL for the Hausdorff measure restricted to kind of the set of points touched by this line, if you really think of it as a line. So, and now we can give a rigorous definition, namely we define L to be H1. This we can, okay, and now we will have dx1 of applied to V plus H2, and then the same thing. Okay, but then if one does that, that doesn't quite work out, because if, okay, let's say H were just simply 1, then that expression is going to 0, but the whole thing should be parametrization invariant. So what one has to do if one does this is actually divide by the norm of V here. And that's really because we write this expression instead of an integral. So usually the integral of one forms would be gamma, like, let's say dx fx. That's really the integral from 0 to t, 0 to 1 of derivative of gamma, so gamma dot t f of gamma t dt. And because of this derivative, this becomes parametrization invariant, but this, if we just change the speed at which we walk along this line segment, that doesn't happen. So that's really the natural thing to look at. So one just writes this expression down for a line for kind of the curve gamma x plus tv, and then one sees that this is actually the expression that one gets. Okay, so let me. And now we want to check those two conditions on, namely, we want to calculate the, let's say, the second moment, because it's Gaussian, so we don't need to, I mean, that the second, if we get it for p equals 2, we have it for higher p as well. So what we want to find is h. Okay, now we have this tested against this line segment, and this squared. Okay, and okay, if we look at this definition, so these two we take to be independent Gaussian free fields, so there will be no interaction term, or kind of no term which has h1 and h2 showing up. So what one gets then is that this is actually G integrated against DHL x comma y by definition, and okay, and then we also get kind of a 1 over v. One sec, let me. Okay, so yes, so that's exactly what one gets, plus a constant, since we have this twice from the other Gaussian free field as well. Okay, and this is the same as the integral, well, from 0 to size of v, g of x plus, okay, now there's a, okay, y1, y2, so x plus SV x plus t okay so we fixed one line segment, and then this guy we just bound by 1. Yeah, so well, right now I'm slightly unsure if there's actually too many V's hanging around or not. So, but I think that, yeah, that should be the right thing. That's the direction, and that's how long we go along the direction, and that goes to 0 as, okay, dt ds. Oh, yes. What? C1b. Ah, okay, that's the. Ah, no, okay, so there's no beta, so that was kind of the story why one. Okay. So which expression is it? So which expression is the confusion here? So 2 plus, no. Right, I mean, okay, so we have, okay, let's say our curve has, right, we have a triangle. So, okay, so we have a triangle, we have some points. So first we have gamma at time 0, let's say, S is 0. And that's the origin, okay. And then a good approximation to the triangle would be the straight line. I mean, it's kind of good because it's here. When we don't, what's the mistake that we make? That's kind of this interval, and that mistake can be bounded by bit what? Okay, what's that the one derivative exists and the second one is beta Hölder continuous. The first derivative is beta Hölder continuous. Yes, yes, that might very well be the case. Yes, okay, modulo that. Okay, modulo that thing, and I'll think about it. Okay, but this, okay, to come back, so this is the logarithm of, okay, these x cancels, so we have s, and there's a double integral, s minus t times v divided by norm of v. And okay. Okay, and right now I'm starting, I guess, to be tired, so okay, and then, okay, this is here there would be an absolute value, so this guy can't, here, if we get an absolute value here, we don't have anything. So this is the same as the integral from 0 to norm of v, 0 to norm of v, logarithm of t minus s. So the first integral is almost of order 1, so this first guy is certainly integrable and logarithm barely blows up, so it's we can bound it by v to the power something smaller, so smaller than 1, so it would be 1 minus epsilon, and then the other integral gives us something of order v as well, so we get 2 minus epsilon, and this should be exactly the bound that we want. So we have a 2 here. Yes, so if alpha is almost 1, then we get exactly what we wanted. Now for the second guy, so actually the second bound is not so trivial to get. What one gets is, okay, so I think, what time do we have? What, doesn't anyone have the time? Oh, okay, so maybe kind of quickly. So already yesterday we saw in the lecture that what one ends up is kind of integrating. Let's say we approximate g by, g epsilon. Then what ends up is kind of integrating dx squared of x comma y dx dy. And here we have these triangles. And we want to get a volume bound. And so, okay, one thing, let me first rewrite this. This we can write as indicator of the this triangle, then applying kind of the convolution operator d xg to the indicator again of that triangle. So, and okay, so the first attempt would be to kind of try to by hand calculate this thing, which becomes very painful. And somehow it's actually quite subtle that this thing converges. But what one knows, what one knows is that this is a Calderon-Siegmund operator. Convolution with kind of the second derivative of the Green's function is a Calderon-Siegmund operator, so it's not bounded in L1. And the not being bounded in L1 is exactly why kind of a brutal calculation here will not work. And one has to actually use that this thing is cancels itself. So it's a bit like integrating, it's exactly like integrating x over x squared in one dimension. And so especially these things are Calderon-Siegmund operators, and it's kind of a standard theorem that then this approximation is actually continuous in LP. One sec. So, and then, okay, from this expression, one uses Hölder. So one gets 1 LP, and then here one gets a indicator of LQ because this guy is bounded in LQ. Yes. Question? Or not a question? Tom? Was it a question? Okay. Yeah, so, and actually, if you write this thing down explicitly, I mean, I've tried very hard, so it's not, I mean, to me, it's really not clear how to see it without kind of relying on somehow stronger tools. So in case someone manages to do that, please let me know. Because it's quite annoying. So if you think, so first you get these line integrals, right? So one thing that you get is you have this dp, and then you have this integral over p, and here that the first guy doesn't give you any problems. So here you can just use integration by parts, and then here get the x, let's say, and then dy. And the dy is kind of a contour integral. So, but you are kind of on these triangles. So what you're doing is you're putting your singularity somewhere, and then you're first integrating the volume, which is not a problem, but somehow, if you want to decompose this guy, it's not so clear how to nicely do that. But on the other hand, Calderon-Siegmund theory is a really nice theory, so it's nice to have a look at that. Okay, so I think time-wise, I'm already way over time. Are there any questions? Okay, so I guess that's a no. Then thank you.
Good afternoon, everybody. Welcome back. It's a pleasure for me to announce the fourth lecture of Professor Martin Heyer on the course on Young-Mills progress. Thank you, Martin.
Thank you very much, Paulo. And well, thanks a lot to all of those of you who are staying until the end. So yesterday we discussed about what is sort of a nice state space in the two-dimensional case for this process. So let me just write down the SPD that we are sort of interested in. And so again, this is this dA star of the curvature of A, and then there is this de Turk term, which is a dA d star A. And then we have some kind of space-time white noise. And yesterday we discussed these kind of spaces of distributional connections that are kind of nice and that are such that in 2 dimensions, the torus, you can actually, if you plug this equation into the whole machinery of regularity structures, it gives you a process that's in some sort of negative Hölder space, but actually we know that it differs from the linear guy, so the linear guy being, say, just Laplacian A plus Xi and then there is stuff here. So the solution to this guy here, which is just a Gaussian process, which basically looks like the free field. Yesterday we argued that this guy actually belongs to one of these nice spaces of distributional connections. And then since the difference between A and the linearized guy is actually a function valued process, well, the difference also belongs to these spaces of connections, and therefore A itself belongs to that space. And so you can actually remember, so now we've seen that if you take this space of connections and you quotient by the alpha Hölder gauge transformations, then this is actually a nice state space. So let's give it a name. So let's say O alpha, like space of orbits. And now what we would really like to know is that A actually defines a Markov process on O alpha, right? So we have a canonical projection, right? So that goes from A omega alpha to O alpha, which is just, the quotient map. So we have this canonical projection, and we have a process, we have a Markov process up here in omega A. I mean, of course, there's technicalities about the thing possibly blowing up in finite time and stuff like that, but I'm just going to ignore this. So we have a process up here, but now in principle, you can have two different initial conditions here that get projected down to the same guy. And then what you want to know is that, well, if you start the guy from the two different initial conditions and you look at the two solutions and you project the two solutions, then you better get the same thing. Right? Because otherwise it doesn't canonic, right? So you have a process here, you want to turn it into a process here. If the property I just mentioned isn't true, well, then at least you don't get a Markov process here, right? So you can, of course, always take the process here and just project it, but they just wouldn't be Markov, right? So that's the property that I want to discuss today. Before I'm going to do this, I wanted to just say a little bit more about the three-dimensional case. So remember yesterday I mentioned that this whole thing works very well in 2 dimensions, but it really doesn't work in 3 dimensions. And I think in the exercises this morning, you've seen probably, I think Harpreet has probably discussed that the 3-dimensional free field really cannot be restricted to lines because, well, the covariance is essentially 1 over x, and 1 over x is a non-integrable singularity in 1 dimension, obviously. Whereas the 2-dimensional free field has a log x kind of correlation, and log x is perfectly integrable in 1 dimension, right? That's essentially the reason why you can lift the 2D free field to lines, but not the 3D free field. So this kind of construction doesn't work. And actually, well, since you can't restrict it to lines, one doesn't really expect to have to be able to find any state space in which the process lives, the 3-dimensional one, and so that these Wilson loop observables are somehow well defined on that state space. Now, there might be some kind of renormalized Wilson loop observables. So if you look at the literature, so there are certainly some papers where that sort of claims are made. The arguments are not super convincing. So I don't know. I wouldn't really hold my breath. Maybe there is a way of defining renormalized Wilson loops in 3 dimensions, but it's not clear at all to me. So what we'd want instead is have a state space which is, sort of the next best thing. So you want something which is big enough to actually contain solutions, and then maybe have some kind of a smoothened version of Wilson loops that are defined on the state space. And so what is a smoothened version of Wilson loops? Well, one thing you can do, you see, the point of Wilson loops is to get gauge invariant observables, right? So one thing you can do is you can start, say you have a connection A, but maybe the components are distributions, so it's not really a connection, but you have an A, and you want to define something a bit like a Wilson loop observable. So one thing that you could do is you could look at this equation here, right? Just the heat flow, if you want. Right? So that's the Young-Mills heat flow. Now, the Young-Mills heat flow sort of preserves gauge equivalence in the sense that if you have two initial conditions that are gauge equivalent and you run them under the Young-Mills heat flow, then the solutions are again gauge equivalent, right? So it sort of preserves equivalence classes. And it's parabolic, right? That guy is a parabolic PDE, so you can feed it pretty much anything as initial data and it's instantly going to be in C infinity, right? So then one thing you could do is you can say, oh, well, okay, I don't have Wilson loop observables, but what I can do is I take a guy in my state space, an A in my state space, and then I just look at the solution to this deterministic equation for a very short time, like a time epsilon. And so it doesn't change the thing much, if you want, but it regularizes, right? So it's a little bit, you know, normally one standard regularization that one uses a lot, actually, especially in probability theory, is, you know, convolve with the heat kernel for a very short time epsilon, right? You take the sort of the heat kernel with t equal epsilon, and then you just hit whatever singular guy you don't like with the heat kernel at time epsilon, and you get something C infinity. Here, you don't want to do that, right? Because hitting A with the heat kernel does not preserve gauge equivalence, right? So, so solving this equation, if you want, it's like a nonlinear version of convolving with the heat kernel, which does preserve gauge equivalence, right? So it's somehow sort of a natural modification here, which preserves gauge equivalence. And so then you can say, well, okay, so I just hit it with this guy for a time epsilon, and then I have a smooth connection, and then I can just look at Wilson loop observables. Okay. But for this, one thing that you need is that actually this guy is well posed for every initial data in your state space. And so actually, if you go through the whole sort of machinery of regularity structures in 3D, it tells you that you get a process which belongs to C minus a half minus kappa for every kappa. But you actually get that process only if you start from an initial data which is not an arbitrary guy in here, but the initial data has to already differ by something which is better than C minus a half. So remember, so let me call again Z the solution to the linear equation, right? So say dtz equal Laplacian z plus xi. So that's the linearized guy. And so the initial data one has to take for the machinery to apply is actually something which differs from z by a guy which is in some C eta for eta bigger than minus a half. Okay. So in some sense, you can't start it with arbitrary initial data even. You have to start with an initial condition that actually already looks like the way the solutions are going to look like later on. Right? So initial condition that looks like the stationary linearized guy. So that's basically a free field plus something which is strictly more regular, right? With regularity strictly bigger than minus a half, whereas this guy has regularity strictly less than minus a half. So why is that? So, you know, why don't we have a decent even solution theory in that space? It's because remember, one of the nonlinear terms here was of the form, some bilinear form applied to dA and A, okay? So now these spaces, these negative Hölder spaces, right? So they have the property that if A, say, belongs to C minus beta, say, then if you look at the heat kernel the heat semigroup applied to A, and you look at, say, the L infinity norm, right? Or, right, yeah, the L infinity norm, then that typically, for small time, it's going to blow up because I take beta positive. For small time, it's going to blow up, and it's actually going to blow up like t to the minus beta over 2. Okay. Now, and you see in particular, for example, you see if I take initial data, which is a delta function belongs to c to the minus dimension of your space. And then here you have the t to the minus dimension over 2, which is indeed the supremum bound on the heat kernel, right? So this is consistent with that. And the same thing for derivative. So if whenever you take a derivative, you lose, right? So here you get like t to the minus of beta plus 1 over 2 or something. Okay, so you have that sort of bounds, and these bounds can't really be improved, right? These are really sharp because they're almost the definition of these spaces. Right? It's almost the definition of these spaces. And so now, for short times, you would expect this guy to look more or less like PTA, right? Because at the end of the day, our equation is some kind of perturbation of the heat equation. So, we can be bold and just pretend that everything else doesn't matter, including the noise, right? So that's the best you can hope. Right? The best you can hope is that that guy behaves like solution to the heat equation. You certainly can't hope better. Right? Now, if this guy has a supremum norm that's like t to the minus beta over 2, this guy has a supremum norm that goes like that, then it means that this bilinear form here, right? Well, the best you can hope is that it has a bound which is sort of like minus 2 beta plus 1 over 2, right? Because it's just the product of these two guys. And you really can't hope to improve that. And now, if you think of, how are solutions even defined, that even if, forget about the noise, forget about renormalization, forget about all of that stuff, right? Just look at the deterministic equation, right? So forget about psi. Just take the deterministic equation. You do one round of Picard iteration. What do you do? The first round of your Picard iteration gives you just the heat solution to heat equation. And then the second round, what you want to do is you take this, you stick it into the nonlinearity, and then you hit it again with the heat kernel, right? And hitting it with the heat kernel is some kind of integral in time, right? Now, this guy, when I stick it into the nonlinearity, well, I get something of this type here, of this kind of regularity here. But now, if you see that if beta is equal to a half, right, then I get 2 times a half, which is 1, plus 1 is 2 divided by 2 is 1. So you get 1 over t, which is a non-integrable singularity at the origin. So you see that actually, if you take an arbitrary guy in that space, the second round of the Picard iteration already, can't be controlled because you actually end up with a non-integrable singularity at the origin, right? So this forces you to take beta strictly less than a half if you want to have any chance of even solving the deterministic equation, right? So you have this parabolic equation. So even the deterministic equation, the claim is that if you start with initial data, arbitrary initial data in C minus beta for beta bigger than a half, it's just not well posed. So it's, you can actually, I think there's even a little recent paper by Ilya where he, provides like counterexample. Right? It means that like you can just find a sequence of initial data which is smooth and which converges to 0 in that space, and so that the solutions blow up. Right? So that kind of thing. So this equation, even the deterministic part of the equation, is simply not well posed in these spaces, and therefore you can't hope you make it just much worse by adding that space-time white noise and adding all the renormalization business on top. You can't hope to have a better solution theory than the deterministic one, right? So that's a problem. So that's sort of the first problem in 3 dimension, which is sort of one of the main problems. But then somehow you have to be able to get around that, because, like I claimed, that if you actually start with that sort of initial data, then you're fine. And the reason why you're fine is that if you take for A, not an arbitrary guy in C minus beta, but you take an actual, a realization of the free field, then you can actually do a calculation and you find that there are actually some stochastic cancellations in here. And so this guy actually behaves a bit better than what you'd think, right? So if you actually start this with an instance of the free field or something that looks like Z0, right? Well, then your Picard iteration works, but it works for probabilistic reasons, right? So it's not for analytic reasons. So in particular, there's actually, so even, like improving on that norm doesn't help, okay? So the theorem, I think actually even Ilya's theorem says that, but there is an analogous theorem by Terry Lines from 94, which says that, when he argued for a rough path and the fact that the Levy area should really be considered as a sort of additional analytic data, he wrote a little paper which basically said that it's impossible to find any Banach space which on the one hand is big enough to contain realizations of Brownian motion, and on the other hand is sufficiently small so that the Levy area is well defined. Right? So it's just impossible to find any Banach space which has that property. And here, well, in the little paper by Ilya, there's essentially the same statement. It's impossible to find any Banach space which is big enough so that it contains realization of the free field, and which is small enough so that the Young-Mills heat flow is well defined on it. Okay. So that seems like a problem. But of course, the operative word here was Banach space, right? I mean, it's like basically it's not possible to find a linear space of initial data, a nice linear space, so that this is well defined. And so you can hope to find a nice nonlinear space of initial data, so that this is well defined. And so then what you end up doing is you basically postulate that this guy is integrable, right? So what you say is you just look at initial data, which is of the form, well, A itself should be in C minus a half minus kappa. And then if you look at the derivative of PTA, and you hit this into the bilinear form that shows up on the right-hand side of the equation, and then you look at the behavior as t goes to 0, then you want this guy to be, well, to actually have so. Right, so you want a better weight than that. Right, so I don't remember exactly which exponent we can get away with, but you want something like this, right? Like t less than 1, and sort of L infinity norm finite. Right? So you basically just impose something like this, and you can check that for the free field, some bound like that holds. And then that gives you a space of initial conditions, right? It's some sort of nonlinear space of initial condition. It's a subset, right? It's some sort of weird nonlinear subset of that guy, but it's a nice metric space in its own right, right? So you can, out of this, you can, of course, you can build a distance function on that space, and it's sort of reasonably well behaved. The other problem, and actually, so this, just wanted to say that, okay, so first, if you have that sort of control, then that is good enough then to close fixed point arguments. So you can show that at least the deterministic Young-Mills heat flow is well defined for all initial data in that space. And it has kind of nice regularity properties as a function of the initial data. The other thing I wanted to mention is that actually there's a recent paper by Kao and Chatterjee where they argue for sort of what could be plausible state spaces for Young-Mills theory in dimensions 3 or 4, and they propose exactly that kind of space as well. Okay. Well, actually, they don't propose this directly like this. So what they say is that you can actually, in some sense, you take smooth functions, right? So you can say something like that. So you have t here. You have functions from t to at, which is such that at plus s solves Young-Mills heat with initial condition as, right? For every s, I mean at time t, for every s and t. So you look at sort of basically all smooth functions of time that solve the Young-Mills heat flow, but so that you don't impose anything at time 0, right? So they could actually come down from infinity or something. They could do weird stuff at time 0, right? So our spaces, I claim, are perfectly nice elements of such a space, because I have at time 0, I have a distribution. The distribution is nice enough so I can make sense of the Young-Mills heat flow, and therefore then for every positive time, it's a smooth function and it just solves that parabolic PDE. And so you can just take that point of view backwards and can say, well, my state space, if you want, would just be, I have this second fictitious time, and it's just smooth functions from R plus, functions from R plus into smooth functions or smooth connections, which solve the Young-Mills heat flow. And well, there's natural equivalence relation there because that guy preserves gauge orbit. So you just, if at any time they're gauge equivalent, they actually have to be gauge equivalent for all times. You can show that. And then you can just take this as your somehow spaces of distributions, if you want, right? So for usual distribution, it's kind of the same thing, because you could define a distribution by simply saying, well, I hit it with a heat kernel, right? Then I get a smooth function. And so I could take this, I could define distributions as simply smooth functions, like all solutions to the heat equation, without saying what it does at time 0. Then I actually get a bit more than just regular kind of normal distributions, but it would be some sort of extension of the notion of distribution, right? Like sometimes people do that. Okay, so that's the way you sort of build some kind of a state space in 3 dimensions. So then you have an equivalence relation there, which is the one I just mentioned, right? So you have the natural notion of gauge equivalence now is that 2 guys are gauge equivalents if when you feed them into the Young-Mills heat flow, they become immediately gauge equivalent at positive times. And there they are just smooth functions, so it's clear what that means. It's still a bit problematic because it's not, there are sort of technical difficulties to do with the fact that if you want to define an actual Markov process on the space of gauge orbits, then, there is this problem which Paulo already mentioned on Monday, which is that things could explode in finite time. And they can explode in 2 ways, right? So they can explode because, well, A simply goes off to infinity like that, or it could explode because it kind of goes off to infinity like that, in the sense that, in the space of gauge orbits, it may not explode, but in the space of connections that you're quotienting in order to get your space of gauge orbits, there it might explode. Right? It might just explode along a gauge orbit. Right? Since they are non-compact, you can do that. And so that's sort of a cause of endless technical difficulties. And so that's why you have to, the state space we actually end up choosing has an additional bit that kind of allows you to control a little bit, to say that when something like that wants to happen, you can kind of restart the process somewhere else on the gauge orbit, and you can make sure that essentially you fiddle with the process to make sure that only this can happen, and you prevent this from happening without changing the quotient process. Okay, but that's mostly a technicality. It's sort of a very annoying technicality, but in some sense ultimately not such an interesting technicality. Okay, so that's about the three-dimensional state space. And so now I want to, well, maybe first, are there any questions? No? Okay. So maybe now I want to argue actually, that the process that you end up building is sort of gauge equivariant, right? So that it has that property that if you start from two different initial conditions that are gauge equivalent, then the laws of the solutions that you get are the same after projecting onto the space of gauge orbits, right? After quotienting by the gauge group. Now, so let's first do a calculation. So what I want to do is I want to basically guess how, the following thing. So I have an initial condition A, say A0. And so then here I have the same initial condition, but on which I've acted with an element of the gauge group. Okay. And so now here I have the solution to this equation. And now what you'd like to do is you would like to find a process G that depends on T, right? So here you have AT. And now here I say I write BT to be AT acted upon by a possibly time-dependent gauge transformation, right? It doesn't have to be the same as the one at time zero, so it's allowed to itself evolve over time. And you want to do this in such a way, so you want to find the GT in such a way that if you look at that process here, then that process solves the same equation as the one that A solved, right? Ideally, that's what you want. Okay? So because you want to say, right, we want to say that the guy started from this point has the same law after quotienting out gauge transformation as the guy starting from this point. And so that basically means that if I start from this point, I just want to be able to find some kind of maybe random and time-dependent or whatever gauge transformation, right? So the gauge transformation doesn't have to be fixed because I just want to be on the same orbit. So it can be anything, but I want to find some kind of maybe time-dependent and random gauge transformation that maps the solution starting from here to the solution starting from here. Right? And actually, in some sense, the mapping doesn't even need to be pathwise because it only needs to be the same in law. So I could possibly also include some measure-preserving transformation of the underlying noise, right, of the underlying white noise. So, and that's what we're actually going to do. So because you see, so one thing I could do, because you will actually end up with seeing, so I already mentioned that yesterday, I think, you sort of end up seeing the noise conjugated with some gauge, some element of the gauge group, and now conjugating with an element of the gauge group is an orthogonal transformation in L2. And so, you know, the white noise conjugated by this is again a white noise. Okay? So what you really want to do is, you see, you want to guess the correct GT so that if I transform A with this time-dependent GT, then maybe the equation for B doesn't need to be the same as for A. It's allowed to be the same as for A, modulo doing a measure-preserving transformation of the noise. Right? So that's also fine. Okay, so is it somewhat clear what we're trying to achieve here? Right. So let's just do the calculation. You see, you'll see how it looks. And I'm going to make sign mistakes. So signs in the calculation are going to be somewhat random, and I'm just going to fix them at the end, so that because I know what the answer is. Right. Okay. So let me write. Right, so we write BT is AT GT, which is, and now again, I write everything is written sort of in coordinates. I fix my coordinate systems, and so I pretend that all the G's are matrices and so on, and so I don't worry about, multiplying elements of the group with elements in the algebra or stuff like that. Okay, I just do everything as if it was a matrix group. And if you want fancier notations, one can do the same calculation with the fancier notation. So here, remember, this is basically GTA GT inverse minus dGT times GT inverse. And that D is not a D in time, but it's a D in space, right? So that's the differential of G in space. So maybe in components, right? So if I remove the T index and I sort of put a spatial index in there, then the I has a spatial index, right? And this is somehow the derivative of G in the ith spatial direction. Okay, so in components it looks like that. And these guys are matrices. Okay, so that's my B. And yes. No, okay, so simple translation doesn't work. And the reason why simple translation doesn't work is because of this de Turck term. Right? So if you didn't have the noise and you didn't have that guy, for this equation here, simple translation works. Right? So this equation, if you stop here, then that equation has the property that actually, if you start with AG, then I can just look at BT, which is AT with a non-time dependent G, which is somehow the same G, which doesn't depend on time, and then that guy just solves the same equation, right? But because we've added this de Turck term here, that messes up that calculation. I think that's kind of clear because the interpretation of the de Turck term is that here dynamically at every point you add an extra term that sort of pushes you somehow in the direction of the gauge orbit, right? And so then, of course, that's going to influence, right? The term that you're adding here is not going to be the same as the one you're adding here in general, right? And so, and therefore, there's basically no reason why. Okay, thanks. Right, so let's just do the calculation. So what is dTB, right? So on the one hand, you get dTA G inverse, and then you get a you get the time derivative of this expression, but the time derivative of this expression we've actually seen, we've done a calculation already that kind of tells us what the answer is. Because remember, when we did the calculation that tells us what are the directions that you can go in here, right? So what we said here is we look at the map J goes to AG, and we basically differentiate in G, right? And then we saw that the direction in which it pushes you is actually the dA of, you know, whatever the infinitesimal change in G you're taking, right? And therefore, that's exactly what's going to happen here, right? So if I take the time derivative, on the one hand, I have the time derivative of A, so that's like that. But then on the other hand, all the additional terms that I get are exactly the terms that I would get if I freeze A and I look at, you know, what is a sort of time, a slight shift. You know, how does this term here, which is just the AG, how does this term here change under a slight change of G, right? And so we know a priori that this is going to be dB of whatever the change of G is, which is the TTG G inverse. This G inverse thing is just because now it's not at the origin, but it's at G somehow that we take the derivative. Okay, so we get a term like this. And then the DTA guy, we know that, well, so you have these three terms, right? So for the first term, we have the fact that that guy is actually gauge invariant. And so that tells us that here we just get a minus dB star FB. And if we only had the first term, then this would just be that. And therefore, right, and so that would be the remark that you made, right? If we only had the first term, then this guy would just be that. And therefore, if we wanted B to solve the same equation, all we have to do is set BTG equals 0. And then this term here drops as well, and we get the same equation back. Okay? But now the equation is different. We have these two extra terms. And so we have to, you know, find out what happens with these two terms. So for the first term, I get a minus. Well, I have my G, dA, d star A, G inverse. Right. And then what else do I have? I've got the same with the psi. And so I have a plus G psi G inverse. And there the idea is to say, well, this guy is equal in law to psi itself. Right? But at least here I'm being somewhat formal, and this is actually going to be a bit tricky to justify, right? But if this were really space-time white noise, right, then this is just the G itself. Okay, this is also going to be sort of slightly self-consistent, but at the end of the day, we're going to derive a PDE for G, right? Because we're going to identify DTG with, you know, some term here in order to make things cancel out. So we're going to derive a PDE for G. And so the G guy is going to be adapted to the same filtration as the A guy and the B guy. And so then here, this is really something like, you know, you have an eta integral of a guy which is orthogonal and adapted. And therefore, you know, you just get the same Wiener process back, right? So you have a cylindrical, you can view your space-time white noise as a cylindrical Wiener process. And then this here just corresponds to integrating some, you know, orthogonal, adapted orthogonal guy against your cylindrical Wiener process, and then you just get the same cylindrical Wiener process back in law. Okay, but only in law, not pathwise. Right? So here, this guy, you'd expect it to be the same in law as that guy, so that's good. And now, of course, we still have this term here. Minus dB, dg, g inverse, okay? And so now what we want is we want to transform this guy into something that kind of looks the same, but with a b. So, so on the one hand, right, I want to basically sort of pull these derivatives out. So let me just write this out in more detail. This dd star A, right, this is really, this d star is some kind of divergence, right? So what this guy looks like, it's really something like dj di, I'll say, if we look at the I component here, then it would really be a di dj of aj, and minus or plus, right? So the A guy, the differential in A is the derivative, the usual derivative, and then there is the A itself. And so you get an AI, dj AI, and then a G inverse, and then plus, these two terms here. So this term here, I've just written it out in coordinates, right? So this is just rewriting what this term actually is. And now you can sort of, try to pull your G's sort of through. And so I'm not going to do the calculation because, well, I'm going to make mistakes anyway. But what you end up with in the end is, well, the term that you want, right? So you have dB d star b. But then you have some discrepancy, because if you do that calculation, you just find that, well, it's just not equal to that, and you have a couple of extra terms that show up. And the extra terms that show up are, they're all of the form dB of something, and it's dB of, on the one hand, let's see, there's a d star of dg inverse, probably with a minus here. And on the other hand, you have a term which is the lead bracket of b, and there. Okay. So you get two terms like this. Okay. It's not super important, what it is. At the end of the day, what you find is that you derive an equation for G, right? So you just say, so here you have dB of this dt GG inverse. Here you have a dB of something else. If you want this to cancel out, well, you just set dtg to be equal to what's inside here, right? So if I set this guy to be equal to that, then this term cancels out this term. And at least formally, if I believe this equality in law, then the equation that's written here for B is the same as the equation I started from, which was the equation for A, right? So you get an equation for G. It doesn't matter too much what it is, right? So it's just the equality between these two terms. The important thing is, on the one hand, so what do you notice? So you notice that it's actually elliptic, because if you look at this term here is basically a Laplacian, right? This time d star d is really a Laplacian because G is a scalar function. It's not a, I mean, it's a matrix valued guy, but it doesn't have components, right? There are no GIs. So this guy is really a Laplacian. But then you have additional terms. You have this additional term, and you have a term where this derivative here hits that guy, which is some kind of quadratic term in the derivative of g. So it looks like some sort of KPZ equation because of the quadratic term in the derivative of g, with, you know, a source term like this. So in some sense, the driving noise, right? Like G solves some kind of stochastic PDE, where the driving noise is the B guy itself. Okay. If you look at the sort of regularities that show up, then you find that this term here is actually already borderline ill-posed, because B has regularity -0.5. That means that because of parabolic regularity, G would be expected to have regularity 3.5. That means that the derivative of G would have regularity 0.5. And so here you have again the problem that you're multiplying a guy that has regularity just below -0.5 with a guy that has regularity just below +0.5. So even the equation for that G is a priori ill-posed. Okay. But that one, it turns out that this term has a kind of nice structure. And so this piece of ill-posedness is somehow benign. So it doesn't lead to any kind of renormalization or anything like that. Okay. And so even though it is technically still ill-posed, we're just going to pretend that the equation for G is perfectly well-posed. Okay, so I'm not going to argue anything about renormalization of the equation for G, because that renormalization constant is 0. Okay, so that was a formal argument of why the thing should be gauge invariant. Right? And of course, that argument has to work, because that's sort of how we, you know, why we chose the Turk term of that form in the first place. Right? So something like this has to work. But now if you want to make that argument precise, then you actually slightly run into trouble. Because you see, what happens if you actually make this precise? Then what you find is that, well, what you're really solving is not this equation here. Right? So what you really do is you're mollifying the noise. And then I mentioned yesterday that in order for this guy to converge, actually you have to subtract a term which is sort of proportional to A here. Okay. So this guy here, that should really be xi epsilon, not xi. And then there should be this extra term, which is, you know, you have an extra term, which is a -c epsilon, and that guy gets conjugated with G, right? So it's a G inverse. Now, you would like to say, so now there are two things that break here, right? So on the one hand, okay, so the dTg, we still keep it the same, right? So this guy is going to cancel out this whole thing. And so the equation for B that we have is you end up with dTb is equal to the thing that you want, dB star curvature of B. Then you have this, the Turk term, dB d star B. But then, and then this guy cancels out this guy here. But now here, it's already a bit trickier, right? Because we have a G, psi epsilon, G inverse. And now the thing is that you see G was orthogonal in L2. But now the psi epsilon no longer has L2 as its Cameron-Martin space. So this guy, while formally conjugating with G, keeps white noise invariant, but it doesn't keep a mollification of white noise invariant. Right? So this guy is not going to be the same in law as psi epsilon. Right? That's just not going to be true. The other problem is that here, right, we want to get the same equation as the one for A back. Now the equation for A has now this minus C epsilon A. So we want a minus C epsilon B. But this guy is not B. Right? This is just the conjugation of A with G. Remember, B is that guy minus this. And so you have an extra term now that shows up. Because so this guy is just B plus dGg inverse. Right? So here you have a minus now, minus C epsilon dGg inverse that shows up. Okay? So now the equation for B is that one, whereas the equation for A was that one. So now on the one hand, just because that guy, well, we sort of, okay, so the B was just obtained by hitting with G. So a priori, we sort of know that this guy has to converge to a limit as epsilon goes to 0. But we don't know anymore, right? So now there's no reason anymore that even if that guy has a limit, which it sort of has to, there's no reason why the limit of that guy should be the same as the limit of that guy, right? It's just not the same equation anymore. And it differs in two ways. On the one hand, we have this additional term here. And on the other hand, here we have sort of a mollification of the noise that's conjugated with G. Whereas in the other one, well, this psi epsilon, I could view it, if you want, as conjugating white noise with G and then hitting with a mollifier. Right? That's the same in law. But you have to conjugate before you hit with the mollifier. Right? So what you would like to say, right? So if psi epsilon is, say, rho epsilon convolved with psi, then here you would have G rho epsilon convolved with psi G inverse, whereas the psi epsilon there in law would be the same as G psi G inverse, but then convolved with epsilon, with rho epsilon, right? And these two are, of course, not the same. Now, formally, if epsilon goes to 0, this should be like a delta function, and they should be almost the same. But of course, all this thing is super singular, and so there's no reason for these guys to converge to the same limit, if they converge at all to anything. So, right, so now the hope is that we've messed things up in some way here, right? We have a discrepancy here, because these two are different. And we have a discrepancy, because there's this extra term here. And now the question is, do these two discrepancies sort of cancel out? So now in principle, you can just apply the whole regularity structure business to this equation here, right? So you just take this equation for B, because there's a G in it, but G solves an equation that only depends on B, and so it's like it's a pair B and G if you want. So you can look at this equation here, and you can apply the whole regularity structure business to that. Now that's more complicated because the equation for G, right? So G is a more nonlinear sort of object, so you have to fiddle a bit more with the theory in order to kind of fit it into that. But that's fine. You can do that. And when you sort of stick this into the theory, what the theory tells you is that actually it's possible to find some constant, right? So let me say, so you take dt, say A bar is, I write the same equation. Plus G psi epsilon G inverse minus C epsilon A bar. But then here I write C epsilon hat dg G inverse. Okay? So if I look at this equation, then this you can actually feed it into the whole theory of regularity structures. And the theory tells you that it's possible to choose the C epsilon hat. There is a way of choosing C epsilon hat in such a way that that guy converges to the same limit as that guy. Okay, so that's what the general theory tells you. But it doesn't tell you that the C epsilon hat is equal to C epsilon. Okay. So now, in general, well, C epsilon hat will just not be equal to C epsilon. Okay, so that's just a fact of life. But then what you could do is you could say, oh, instead of looking at this equation with a C epsilon, I look at the equation with a C epsilon plus little c. Okay, you think, well, I'm not really changing anything, but I am changing something because the C epsilon is a very specific C epsilon that's given by the theory that tells me, oh, that guarantees that these guys converge to a limit, and it somehow has the property that, you know, it has the property that, for example, the same C epsilon should show up here if you want the same limit and, you know, that kind of things. So if I change the C epsilon here into C epsilon plus C, then, well, then of course here I get, you know, C epsilon plus C and C epsilon plus C. Okay. But now what the general theory tells me is that actually here I only have to add the C here. And, you know, there is a choice of C epsilon hat so that this guy converges to the same limit as this guy here. Okay. So now if we knew that C epsilon hat and C epsilon, they may not be the same, but if we knew that their difference converges to a limit, right? If we knew that their difference is actually just a fixed constant, then we're in business, because then I could simply choose the little c in such a way that C epsilon plus C is equal to C epsilon hat, and then this equation is the same as that one. And then the general theory tells me that that guy has the same limit as A, and therefore this guy is the same as A. Solves the same equation as A. Okay? And what you actually see from this argument is that, well, there's basically no choice about the little c. Right? So I have to choose. So now assuming, and that's going to be a theorem, right? The theorem is going to be that C epsilon hat and C epsilon, their difference actually converges to a limit. And then you have no choice, right? So if you want, so now what does this tell us? It tells us up here, because of this whole renormalization business, a priori, you had a whole one parameter family of possible notions of solutions, right? Like for STEs. For STEs, you have Ito solutions, you have Stratonovich solutions. You actually have a whole one parameter family because, you know, Ito is like choosing some constant equal to 0 and Stratonovich is a half. You could choose it 1, you get some sort of backwards Ito and so on, right? So here it's the same. You get, a priori, you get a one parameter family of solutions that's indexed by this constant little c, okay? And they're all, a priori, there's no way of distinguishing between them, right? I mean, all of them are equally valid if you want to be candidates for solutions to that equation. In the case of STEs, well, you know, you like Ito theory because Ito integrals give you martingales. You might also like Stratonovich theory because it obeys the chain rule and you can do STEs on manifolds and stuff like that, right? So depending on what kind of symmetries you're after or what kind of properties you want, you might want to choose one guy over one interpretation over the other. Right? So here we want that gauge equivariance. Okay, and the claim now is that there exists exactly one choice of little c here, so that the limit in Markov process here has this gauge equivariance property, right? So that you have actually, right? So in principle, there's one degree of freedom here that comes from renormalization, but the claim is that gauge symmetry actually fixes that. Okay, so there is really just one process, which is the correct process, which has a chance of having, if you want, the Young-Mills measure as invariant measure. Okay, so so here there's a unique choice of that constant that makes this guy have the right property. Of course, the argument here relied on, okay, still have 20 minutes, cool. So the argument here relied on knowing that C epsilon hat and C epsilon converge almost to the same limit, right? So that the difference between these two remains bounded. Or actually, that the difference between the two converges to a limit. Right? That's what the argument relied on. So now I want to show you an argument on how to show that the difference between these two remains bounded. Okay, so I'm not going to show that one can show that the difference actually converges to a limit. But, you know, since there's only 15 minutes left, so what I just want to show you is how do you know, what's the kind of argument that you can come up with in order to show that the difference here between these constants remains bounded. Now, in principle, these guys have explicit formulas, right? So like the theory gives you formulas for these renormalization constants. The problem is that the formulas are somehow horrible. So the formulas, they are, you know, like you've seen in the exercises for Lorenzo's course that, you know, there was a renormalization constant that shows up, and it was obtained by the expectation of, you know, psi epsilon times g convolved with psi epsilon, something like that, right? And then that had some logarithmic blow up, and that's the correct constant that you need to subtract. So here you have similar kind of formulas. So these guys are given by expectations of some expressions. It's just that these constants actually show up as linear combinations of, you know, expectations of a whole bunch of expressions. And there's, you know, like, I don't know how many of them, there's like 20 or 30 or 40 or something. Right? There's like a large number of them. And most of them have logarithmic blow up. So there are a couple that have a 1 over epsilon blow up. And for those, it's relatively easy to see that they actually converge to the same limit, or that the difference remains bounded. Okay, so there's a couple of terms here that give a 1 over epsilon contribution, a couple of terms here that give a 1 over epsilon contribution. Principle, you can, you know, they are like integrals of heat kernel against the mollifier of the noise and, you know, stuff like that. And you can just check that they give you basically the same answer, right? There's some integration by parts somewhere. But then there's a whole bunch of contributions that give you logarithmic divergences. And there's a huge number of them. And then basically what you would want to do is compute the prefactors that show up in front of these logarithms and show that when you add them here, you get the same as when you add them here. And we spend about, I think, a couple months trying to do that and sort of, you know, classify all the ways in which these things can behave and try to figure out how to compute these prefactors. And it's basically hopeless. Okay? I mean, you know, one can maybe do it. One can maybe do it in some sort of computer-assisted way if one figures out good ways of computing these prefactors. But by hand, it's basically hopeless. Okay, so you want a better argument. And so now what I want to do is I want to show you what's the better argument. So what we want to do is we want to assume, right? So assume, okay, and I'm going to, the one thing that I'm going to exploit is that actually, you know, the whole theory is quite robust. And so it tells you could actually stick a sigma in front of the noise. Right, so I told you that these constants, there are formulas for it. The formulas are horrible, but at least one thing that's easy to extract from the formulas is how they behave if I multiply the noise by sigma. Because they're all just going to be some kind of multilinear expressions in the noise. And so you just count how many times the noise shows up in the expression, right? And so then there are some expressions that are quadratic, like the one you saw in the exercises for Lorenz's course. Right? So then, so if you put a sigma in front of the noise, there would be some contributions here that behave like sigma square times something. And there's going to be some contributions that actually behave like sigma to the 4 times something. And there's no cubic term because of symmetries, you know, like third moments of Gaussians being 0, and that sort of reason. And so we know a priori that if I put a sigma here in front of the noise, right, so I could do exactly the same sort of calculations here, and now these constants depend on sigma, but they depend on sigma in a very specific way, right? And they really depend on sigma by C epsilon is C epsilon 1 times sigma square plus C epsilon 2 sigma 4, and the same for the hat guy. Hat 1 sigma square plus C epsilon hat 2 sigma 4. And now I claim that not only the difference between these two remains bounded, actually the difference between these two remains bounded, and the difference between these two remains bounded. Okay? And actually what's really, it sort of has to be, because these guys are all going to be like 1 over epsilon, and these guys behave like log epsilon, so they have different behaviors anyway. Okay, so we have to look at these guys sort of separately. And the other thing that the theory, which is nice about the theory, right, is that it tells you that your solution theory is not just continuous in the initial data and it's continuous in the noise, it's actually continuous basically in all the parameters of the equation. So in particular, it's continuous in sigma. Okay? I can take the sigma just as a parameter of my equation, and then provided I choose these constants like that, the solution theory is linear, is continuous in sigma. Okay? In particular, it converges to something deterministic, which I know, basically, which we control as sigma goes to 0. And that's important. Right? So what we know from the whole theory is that if we take this equation here and we send sigma to 0, then the limit that you get, if you don't have the C here, the limit that you get is the one that you get by simply deleting all of these terms, right? And it's just the Young-Mills heat flow. And same for the equation for A, right? So that's what we're going to exploit. So now assume first that the so the argument is by contradiction, right? And the argument is going to go along the lines of the argument that Harpreet showed you in the first exercise classes about the time reversal symmetry for STEs driven by rough path, which tells you why somehow no renormalization shows up in rough paths typically. So we go by contradiction, right? By contradiction, assume, and so let me just write, say, di to be C epsilon I minus C epsilon hat I. So that's the guy we want to show remains bounded, okay? So assume that the di's go to infinity. Now, of course, it may be that only one of them goes to infinity, okay? So let's say, assume that the sum, so d1 plus d2 goes to infinity, okay? Then what I can do is I choose sigma epsilon such that the difference between these two converges to something non-degenerate. Right? So I can find a sigma epsilon that goes to 0, okay, such that if I look at C epsilon minus C epsilon hat, but that depends on sigma epsilon, right? So now I have a sigma epsilon here. So that this guy converges to some k, which is non-zero. Okay, I can always do that. Well, of course, I can do that only if these guys diverge, right? If they don't diverge, then of course, if I send sigma epsilon to 0, then that difference is just going to go to 0, okay? But if this guy diverges, then I can find sigma epsilon so that this converges to some non-degenerate limit. I can basically choose the limit as whatever I want by choosing the sigmas appropriately, okay? So I choose such a sigma. And then I'm going to consider this equation here. One second. So I want to consider the equation for, right. So I want to consider on the one hand, this equation here. And on the other hand, I want to consider this equation here. Right? So if okay, so now I have to be a little bit careful with the C's, right? So what I want to do is I want to, right, so I want to write this equation as, okay, so now I remove the C. So I look at this equation for A, the one I started from. I have the equation for A bar. And remember that A bar is the guy that I a priori know converges to the same limit as A. Okay. And B is the guy which I a priori know is just a gauge transformation of A. Right, so that's the B. And here, the C epsilon hat, of course, I can write it as, you know, C epsilon minus the D. And the D, well, or here. So C epsilon hat, I can basically write it as C epsilon minus K, right, if I make this choice. So here, I know that the C epsilon hat, this guy, is actually C epsilon minus K. Well, at least for epsilon minus K plus little o of 1, but okay, but it's C epsilon minus K, basically. So now, as epsilon goes to 0, we know that, so let me just, okay, now I'm going to confuse myself. Okay. Right. Yeah. Okay. So, sorry. So we know that A converges, right? So since the sigma goes to 0 and we have continuity of the solution theory in sigma, it just converges to the solution theory at sigma equal to 0, which is the Young-Mills-Higgs flow, the Young-Mills heat flow, right? So the A epsilon converges to A such that dTA is equal to, let me write curly f of A is just that nonlinearity, right? So that's curly f of A. Now, I also know that the A bar, so dTA bar in the limit, right, A bar epsilon converges to some A bar guy, which solves the same thing. Right? But now, what about B? Right, so B, on the one hand, if I compare the equation for B and the equation for A bar, I see that, well, they look pretty much the same, except that here I have a C epsilon, here I have a C epsilon minus K, right? But K is just a fixed constant. And so this tells me that the B, because I know that the A epsilon, the A bar, because I know that the A bar converges to just a deterministic limit, and that I get it with a C epsilon minus K here, then if I didn't have the minus K, then I would converge to the deterministic limit, but with a term plus K times dGg inverse. Right? So the B epsilon converges to B such that dTB is equal to f of B plus K dG G inverse. Okay, so I know this from the fact that A bar converges. Okay? But on the other hand, A converges, and I know that B is just G applied to A. Okay? And the G is precisely the G which is, you know, the correct G which makes the Young-Mills heat flow equivariant. And so from the convergence of A, right, so from the fact that, you know, the B, we actually just derived it as being B. Right, so B was really just A conjugated with G. I mean, G applied to A, and where G solves, you know, that particular equation. So from that fact, and since the deterministic limit, the Young-Mills heat flow, that one actually just solves the, that one is invariant under conjugation with G. So from that fact, we know that dTB solves dTB equal f of B. And now you have a contradiction, right? So on the one hand, from the convergence of A bar, we deduce that the B in the limit solves that equation. And from the convergence of A, we deduce that in the limit, B solves that equation. And then you just have to adjust things in such a way that that guy is sort of non-zero at time zero. You look at what happens at short time or something, and you know, you get a contradiction pretty quickly. Okay? So that argument then tells you that, well, our assumption was wrong, and the assumption was that this guy goes to infinity, therefore it has to remain bounded. Okay, and then one can come up with and that's sort of what I mentioned when I said that actually you use gauge invariance in order to prove gauge invariance. Right? Which is that here we sort of use the gauge invariance of the deterministic guy, which we already know, in order to actually show that these guys remain bounded. And then one can beef up a similar kind of argument to show that they're not just bounded, they actually have to converge to a limit. Like you get a similar sort of contradiction if you assume that there are two subsequences that converge to two different limits. So you can show that these guys really converge to finite limits. And therefore the argument that I mentioned earlier works, right? So we have a choice of little c here, which then makes the, you know, A bar and B solve the same equation. And that gives you this gauge equivariance of the process. Okay? So I think that's basically all I wanted to present. So at the end of this, so what's now left to do? So we've constructed that process both in 2 dimensions and 3 dimensions. So we have sort of a reasonably, in 2 dimensions, we have a very nice state space, which is very natural. In 3 dimensions, it's not quite as nice, but it's at least nice enough so that it doesn't have like horrible pathologies. So you can somewhat do probability theory on it. And then we have constructed, in both 2 and 3 dimensions, you construct an actual Markov process with values in that state space. So there's a bit of extra work you need to do because of this problem of things that could possibly explode along gauge orbits, and you have to somehow just restart it and show that the restarting, of course, doesn't mess things up. But at the end of the day, you've produced these two, you know, that completely canonical kind of process, and which is really sort of unique in the sense, right? So that's this thing about there's a unique choice of C here, so that you really have this gauge equivariance property. So you have that process. Now, ideally you would want to say, well, now I would want to define the Young-Mills measure as being the invariant measure for that guy. The problem so far is that we still don't actually know whether the process we've constructed has global solutions, right? So it may be that along gauge, that even in the space of gauge orbits, it might be that it actually explodes in finite time, or it may, exist for all times, but just not have an invariant measure. It might just wander off. I mean, of course, you wouldn't believe that, and in 2 dimensions, actually, people have a kind of candidate for what the invariant measure should be. Right? So in 2 dimensions, in Gupta back in the 90s, he basically came up with a formula. Well, actually not him. So the formula was derived by physicists already, and so he put it a bit on firmer mathematical setting. So there is a formula in 2 dimensions that basically gives you the joint distribution of Wilson loop observables. Right? So you can, it's a formal calculation you do by just, close your eyes and pretend that e to the minus s of a exists as a measure, and you can actually derive from that a formula for the joint distribution of k Wilson loops. You take k loops and you look at the k Wilson loops of observables. That gives you sort of k random variables. You can look at the joint distribution of these guys for all k's and all loops. And so we have kind of a candidate. So in principle, in 2 dimensions, there is reasonably good hope to be able to prove that the process that we build does actually have that measure as invariant measure. Right? And then in 3 dimension, there is no a priori candidate, so there it would be really new. And so what we would want to do is have some kind of a priori control on the solutions, right? So you would want to know that these solutions not only don't blow up in finite time, but they actually have some tightness property, so that then you get an invariant measure. If you have such a tightness property and you can build an invariant measure, then we can already show that the invariant measure has to be unique. Okay, so basically, so we know already that if the invariant measure exists, it's actually unique. Right? So then the measure is sort of well defined, but we just don't yet know that it actually exists. Okay. So okay, so I think that's a very good point to stop, and well, thank you very much.
Right. Thank you very much, Martin. Questions and comments? Yes.
Thank you very much for the very nice course. My question is about, you might know there are these cancellation identities with which Marte Carenza has proved in 2020. And from what you just said, I understand they are not enough to prove what you want to prove. But I was wondering, the argument that you sketched and the beefing up the argument to show that the difference actually converges to a finite limit, do you see any chance that you could use that strategy to prove that the cancellation identities that Marte has actually give you 0 in the limit? Because I think what he proves is that they give you a finite constant in the limit, but you might be interested in the question if that constant is actually 0. And from what you sketched, it seems to me that you might not be able to use that.
No, well, okay, so
I hope that was a well-posed question.
So maybe, okay. So in general, right? I mean, generally, there's some arbitrariness even in the definition of these constants, right? So like, okay, the way I presented it is that these constants drop out of the theory, but they actually drop out of the theory after you've made some arbitrary choices, right? So you choose some kind of truncation of the heat kernel or something. If you make a different choice, that gives you a different definition of these constants, which then forces you to choose a different C so that you actually get the same process. So the process is still canonical, but right? The way of little c, for example, is not canonical, right? The numerical value of little c has no meaning at all, right? So the numerical value of little c has absolutely zero meaning because different choices of modification or different choices of truncation of heat kernel and so on give you different c epsilons, okay? And it's just that the process that you get then is always the same, because you just choose the little c which compensates for that somehow. And that's sort of a general thing, right? So if you have symmetries, then typically what you can do is you can choose the renormalization in such a way that you have that symmetry in the limit as well. But it doesn't mean that, say, BPH, right? So if you like fix your renormalization scheme, you know, sort of like BPHZ with like this choice of modifier and this choice of truncation of the heat kernel, then of course that just, you know, gives you essentially like a random point in the point of possible solution theories, which has no reason to obey any kind of symmetry or anything, right? So somehow saying that, you know, like differences between two constants are zero or bounded also, I think that's not necessarily a sort of very meaningful statement, if you see what I mean. So it's more about the, I mean, right? Because if the differences is finite or sort of converges to a finite limit, then that means that you can sort of, you know, always just choose a different point in your renormalization group for which, in some sense, the difference is zero, right? Okay. Yeah, maybe I misunderstood a bit the question, but okay.
Right, more questions, comments? Yep.
Thank you for the talk. And I'm wondering, what if you project the noise to the direction orthogonal to all the gauge transformations? Does it make the solutions better?
Yeah, well, right, yeah, so that's a very natural idea, right? So it's, you would say, here, the reason why, right? So you could say, okay, instead of adding this, the Turk term, you say, the reason why this guy was badly behaved is because I had sort of white noise acting in these directions, and in these directions, there's infinitely many of them, and there's no dissipation also. And so what I could do is I could just project the noise at every point onto these sort of orthogonal directions, and then maybe that actually behaves much better, right? So I think that's the question. So if you do that, the equation that you end up with looks somewhat horrible, right? So there's really a bit of a discrepancy here between sort of the geometric intuition and then the analytical tools that you have in order to deal with these things, right? Because, for example, this whole theory knows nothing about geometry or anything, right? So it basically only knows about, you know, write things out in components, put yourself into a chart, and so on. Yeah. It's not intrinsic in any sense. And so things that might look very appealing from a geometric point of view may not look very nice at all anymore. Yeah. By the time you try to feed them into that sort of theory. So in this particular case, you would end up with some sort of multiplicative noise. And that would typically just make things quite a bit worse. Right? So here, we don't really know, because your solution is going to be distributional. And so then you have some kind of, you would want to take some sort of orthogonal projection, but you don't have a good notion of orthogonality, right? Because there's no Hilbert space around in which this, you know, which contains these you could take a negative Sobolev space, but it would have to be very negative, and then that would be rather badly behaved as well. So I don't think it would give you anything very nice. I mean, we've tried to look at that at some point, actually, and it just looks horrible.
Thank you.
Right, thank you. Any more question or comment? Right. Well, if not, so let me thank on behalf of the organizing committee. Thank you, Martin, for this nice overview on progress on Young Mills progress and still open problems. And also on behalf of Mathematical Institute, thank you very much for this nice course. So let's thank the Martin again. Thank you.
Hello, everybody. Welcome to the last talk of the day. It's my pleasure to introduce Professor Maria Eulália Vares from Universidade Federal do Rio de Janeiro, and she will talk about the contact process with dynamic edges or under renewals.
Thank you, Nancy. So first of all, my sincere thanks to the organizers for this very nice school and for giving me the opportunity to be here. And it has been very inspiring days. So my talk today, I don't want to make it technical. Everybody's very tired, probably. And it's, in some sense, a continuation of the talk by Luis Renato Fontes, and based on joint work with Fontes, Marcelo Hilário, Domingos Marchetti, Tom Mumford, and Daniel Ungaretti, and Daniel Valezin. So I will focus mostly on part of these works, but this overall project has been done together with them. So we start by the percolation structure given by Harry's construction of the contact process, so which almost everybody knows, I guess, and also Renato mentioned it. So it could be on more general graphs, but let us think for sake of what we are going to discuss that our graph is simply ZD. So you have this on the timelines of each vertex, you have a Poisson point process that is marked by these blue squares. And for Harry's contact process, they are taught as Cure marks. And on the edge timelines, you have these other Poisson point process that are called N, X, and Y. Since these two are Poisson process, you fix the rate of one of them as being 1, say, and the other one is your parameter in this case. So, and this is the way we want to think about this is this percolation process. So the percolation, the paths are so-called infection paths. They are simply paths which can move on the timeline of a vertex, but they are not allowed to cross any of these blue marks, and they can move to the neighbor only through the errors which are given by the Poisson point process. So in the case of Poisson process, of course, it doesn't matter if they are oriented or not. It's just a matter of changing the rate. But since we are going to dealing with other point process, it's easier to think that they are with an arrow. So they are different independent ones. Okay. So the issue is survival or extinction in the language of Harris. So let us think of survival means percolation. That starting from a vertex, you ask what's the probability to have an infinite path. So we want to consider the same kind of situation, and the only change is that these Poisson point processes are replaced by more general point processes. So, but they keep the same structure, and you ask maybe the same kind of questions. Of course, you do not have any more Markov process, but we are interested in percolation. Okay, so let us focus on two cases for simplicity. So I'm going to think that these point processes that I have are renewal process. That's the simplest case, say, for instance. And we are going to, for simplicity, think that the other one of them is a general renewal and the other one is Poisson. But this doesn't need. We can deal, some results are more general. But for simplicity, we take it like that. And when we change the renewals on the site timelines, that's the one that Renato spoke a few 2 days ago, we call it site renewal contact process. So the errors are still Poisson point process, and the cure marks are IID renewal process with some inter-arrival distribution. So in this case, the process has two parameters, lambda and mu, which is a probability measure, say as some properties to be given. And otherwise, when we think that on the sides we have a Poisson point process, and then I'm going to call, instead of lambda, I will call delta because it's to have a different meaning, and the behavior is of course different. And in the errors are IID renewal process with some inter-arrival distribution, which we need some conditions and which maybe might be different than the ones in the other case. So we have this process and want to, this percolation system, and want to say something about it. We came to this business exactly motivated by some questions on long-range percolation, but this I don't need to discuss it now. So many of the properties that you have for the contact process, which are very nice and very useful, are now lost. Of course, Markov property is lost, but some others might be lost, like FKG property, depending on your measure. So the first questions that we want to ask, the first that Renato discussed, say, let us think the site renewal contact process, and you ask, can you say something about which are the measures for which lambda critical is equal to 0? Remember, for the contact process, ZD, lambda critical is positive and finite. So you have a subcritical region and a supercritical. And here we are asking, when it's the case that you have only the supercritical region. That means that you have survival no matter how small is the transmission rate, that starting from the origin, the probability to find an infinite path is positive for all lambda positives. That was the question that, one of the questions that Renato addressed. So you might ask the same question for the edge renewal, the analogous question, no? So you ask, for which measures can we guarantee that delta critical is 0? That means that no matter how small is the cure rate, you will not have an infinite path. No? That means that you don't have a supercritical region, that everything, it will always disappear, for which. So since I said that I'm going to think of the other process given by lambda and delta as Poisson process, so you have an obvious monotonicity increasing in lambda and decreasing in delta. But it's easier to think about them, especially because of this property. But some of the results apply for more general point renewal process, also for the other case, or edge or site. But then it's not clear that you might have different phase transitions because it's not monotone anymore. No? So we are interested in that. So it's simpler to think about this case. The point is that if you put in this general frame, you want to do something based only on valid for quite general class of measures, you get much less poorer tools. No? So the tools are basically, first tools that work in general, you want to control the gaps. No? You want to say that the gaps are big. That means that when your measure has a fat tail, or that you control the gaps that they are not too big if you have a moment condition on your measure. So this is, so you thinking of the case of mu is a heavy tail, then you need some results on the renewal, stronger renewal, which are not so old, so classical, like and so I put here some reference because some not so much for what I do today, but what Renato mentioned, we use some recent papers of Xi and also Caravena Doni, and also classical papers. So a general ingredient, thinking of the first question, both site or renewal, the first ingredient is that you have big gaps. You know? So that's what is, if you have very big gaps in the cures, then no matter how small is the transmission rate, as Renato mentioned, proved, you do have percolation. So one ingredient that you can think is this, what I call here G. So that there is an epsilon such that for large T, the probability to find this gap, so you have a very big gap from T to T plus T epsilon is fixed, is very close to 1. So this property is used and very important for the results that Renato proved, and it will be also for what I'm going to mention now. So these were the first results answering this first question, and they were presented by Renato. So I just mentioned here. So there was this heavy tail, and I don't need to stay because this was already discussed. So I want to look at the counterpart in the edge case. But I didn't say very explicitly which are the conditions, and the conditions that also Luis Renato expressed the other day in his talk are basically the heavy tail plus some regularity. So, and the important thing is that these three conditions, so I think we already saw them, so I don't need to, A and B, I don't need to spend too much time, some sort of regularity. And here condition C is the heavy tail, and this is a nuisance, but we don't know how to get rid of it, but it's a little bit nuisance. So these three conditions imply G. So this shows that, well, in some cases, some of the results we don't need really in the domain of attraction of a stable, which of course satisfies all this with a fixed alpha there instead of having different lower and upper bound. So this proposition, I think it was a key thing for our for this theorem 1 and theorem 1 prime that Renato already spoke. I want to focus on the edge case. No? But let me, because the conditions are going to be parallel, some of them, not all of them. So the second question, which in the case of site also Renato discussed, was when can we say that lambda critical is positive? So we are answering very preliminary questions about these processes. So that means when you do have a subcritical phase. And one condition was something a little bit more than first moment. So it remains open if first moment is enough. All the examples that we have in the domain of attraction of one, stable one, they are, whenever there is 0, it's infinite moment when it's positive. But we don't know if first moment is enough. So for the moment, this is the best, and this was already discussed. So I am going to go to the case which I'm my focus today, which is in the H renewals. So in this case, let us think that the cure marks, those blue marks, are given by a Poisson point process and of rate delta. And I have the transmissions given by IID renewals, and mu is the inter-arrival distribution. That's the case which I want to look. And this is this joint work with, part of a joint work with Hilario Ungaretti, who is here, and Valesi. So what I'm going to say is maybe somehow counterpart of what has been already said for this site. Let's say one thing. So if mu is the inter-arrival for the transmissions, then I better assume mu is continuous. Otherwise, there might be some strange things like, it's like with first passage percolation. If you have an atom at 0, then you might get the shape is RD. But here is more messy, and it's some pathological thing, because you might explode to infinite in a fixed time. Say, not only, even if your atoms are small, but you might combine two of them, and then at some point everybody gets the same time infected. So, and that's not so nice. So we assume that mu is continuous. This assumption is not necessary for the site because it has a different role. So what we can say regarding the first question, that means when you have extinction for all delta positive, no matter how small is this transmission rate, it destroys your process. You don't have percolation. So conditions are exactly the same as we had in the site case. So if A, B, and C, that's what we know for the moment, and maybe. So the other part about having delta positive, so we have a result which requires only finite first moment, and then there is survival for a small delta. But note that this is, I have a dimension bigger or equal than 2. So I don't know, we don't know if this is true in one dimension, because in one dimension it's more difficult to survive. That's a percolation issue. So this is the second part of the result. And the third, which is very similar to the extinction results that Renato discussed. It's very similar also in its proof, is that if mu satisfies the same condition that I had mentioned before, that means the integral of x times the exponential of theta square root of logarithm with a theta bigger than a fixed constant that depends on the dimension, then you have extinction if delta is large. So this is the counterpart of the one that Renato discussed for site, which was you have extinction if lambda is small. No, that's lambda critical is positive. So I want to give a little bit of an idea of how these proofs go. So my comment, general comment here is just that the item 3 here is really very similar to one of the theorems that Renato proved. The others have a different scheme. One thing that I want to mention, because it bothers me really a lot, because I have been frustrated of not able to say something, is to have general ways of coupling renewal process. Except for trivial cases, it seems quite tough. You know, you want to put one renewal process inside of another one. Of course, there are cases that is trivial, but then they are trivial. And the general results on that seem to be missing. There is a it's a important paper, I believe, by Herman Rost, which gives necessary and sufficient condition to couple, to write one as a sum of the other with some stopping times. So it seems very beautiful, but the necessary and sufficient condition, I have no idea how to deal with that. In any case, even in simple cases. So it's a bit frustrating that one doesn't mean, when I discovered that paper with Renato and Tom, was very happy that maybe can use the paper of Herman, and I was very happy about that. But I don't know. It seems very hard. So I think it's an issue that probably would be useful in many areas. To renewal processes are sometimes difficult to compare them, to couple them. Anyway, that's just a general comment. The other thing, which in fact was one of our main motivations to get with these edge renewals, came from this model. So which was done in the same paper of, with Marcelo, Hilario, Daniel Ungaretti, Valezin. So it's a contact process in a dynamic environment, dynamic random environment. We already mentioned, and Renato had commented on that, about some of the tools that we were using in one of the theorems being similar to tools in contact process in static random walk. So random environment. So this is a dynamic random environment, and this paper, a very nice paper by Linker and Hemenick, recently published, is the following. You think of your dynamic environment is the so-called dynamic bond percolation. So let me say what it means. So I'm going to think of the environment as this process zeta t, takes value 0, 1 on the configurations on the edges. So that means when it's 1, that edge is closed. When it's 1, that edge is open. So there are periods when there is no transmission in that edge, even if the guy wants to infect the other. There are periods when there is. And these are simply given by the dynamic bond percolation. What does it mean? Well, you imagine that at time 0, you just put the Bernoulli measure on the edges. The zeta 0 is just the Bernoulli with parameter p. And then you independently update the edges. They open with a rate v times p, and they close with the rate v times 1 minus p. So v is simply the rate at which everything happens, your clock. So if v is large, you are moving very fast, your environment, but at any time you look, you have the Bernoulli measure. Of course. So the process, the contact process in this environment is the usual contact process, just that it can move only, it can transmit only if the edge is open. So that's what is written here. Huh? So the contact process I'm going to call et t. So it will get cured with rate 1, exponential with rate 1, and transmit with a rate which is lambda times the number of infected neighbors, but they can transmit only if the zeta is open. Otherwise, there are periods when this remains blocked. And these periods depend, of course, depend on p, but they are also speeded up or they are slowed down according to v. So your parameter now has lambda, v, and p. Your model has lambda, v, and p as parameters. And we want to understand this model. So it's clear that you can think of this as an edge renewal contact process, but and that's what motivated us to start study the edge renewals in general. But it's better to use tools which are more exploiting more the contact process, the classical contact process. So because you have a very specific situation. So, and that's what we do, in fact. There are some common ideas with the other, but some tools are. So in this paper, of Linker and Hemenick, they proved several results on this process. It's most of these results work in very general graphs, quite general. Let's not say, I mean, bounded degree, transitive graphs, and so on. For instance, as you can imagine, if you send V to infinity, it should be simpler because it's just averaging everything because it's something. So the other thing is that, well, I mean, it's not so clear how is the dependence of the critical parameter on V. It's clear on P, of course, but they proved several results and a very nice thing. But one of the results was proven only in one dimensional. Was an argument really that demands your graph to be one dimensional. And that is what happens when you fix P and send V to 0. So your dynamic changes, your environment changes very slowly. And so that was our motivation to study this process. So we think you have this parameter V and P, and think of the critical parameter of your contact process as a function of these two. So lambda 0 of V and P is simply the critical value, the inf of this lambda, such that you have a positive probability of survival starting from one single infected individual to have percolation. So this result, I mean, trying to understand this process in what happens in this regime when you fix P and you send V to 0 was, I guess, our main motivation to all this issue on the edge renewals. So what we can prove, then we only consider ZD with D bigger or equal than 2 because one dimension was already treated by them. So what we can prove is stated here, that if P is subcritical, this PC of D means they're critical for edge percolation on ZD. So if P is subcritical, then as V goes to 0, the critical parameter goes to infinity. On the other hand, if P is bigger than PC, it's uniformly bounded. Okay, so I'm going to discuss a little bit what's the idea of that, but let me mention some consequence also. One of the things, general results that they knew is that whenever you fix a V, if you fix V and send P to 0, when P is very small, you fix V, and if P is very small, depending on V, then lambda 0 is indeed infinity. This is a general. So there is a region of immunity. This was already known, that there is a P1 less than 1 in such that, I mean, there is a curve, you don't know what is this curve, but anyway, you have a region where lambda 0 is infinity. So the system is, it's immune. There is no way to no matter how small, well, there's no, for any lambda, it doesn't percolate. You don't know too much about the region, and in their result, they also didn't know anything about P, this value P1 here. I mean, that's about. That's what happens with this when V goes to 0. No? But and why you don't know too much? You know that you don't know if lambda 0 when you fix P, if it's monotone in V. That's not known. But you know something. You know that if you divide by V, it's a simple manipulation with the Poisson rates. then it's monotone. And that allows you to know something about this region, that you might think of a shape like that. So as a consequence of what we prove in this theorem, we know that P1 is in ZD, D bigger or equal than 2, is less or equal than P critical. But we don't know if it's smaller or if it's still not known. So there is this region where lambda 0 is unbounded. In our result is unbounded. It's part 1 of our theorem. And the other region, when it's bigger than PC, it's uniformly bounded. So for the moment, there is still this gap about if there is an intermediate region or not. About that. I should mention here, there is also another recent preprint, which also deals with contact process in dynamic edges by Saylor and Sturm. And it's considering other environments. Okay, let me try to give an idea of some of the arguments involved in these results. I don't want to be technical, and everyone is probably tired. So the first theorem, which I mentioned before, which was about the edge renewal, and I wrote it back here, the statement in pink, so that we remember what I want to discuss. So I'm assuming that mu is continuous, and I have this regularity plus fat tail. No, so A, B, and C. And want to see that delta critical is 0. That means no matter how small is delta, you go extinct. It's a result of extinction. So, and the way, at least the way we dealt with this is the following. Imagine that you don't have cures. So this is the so-called Richardson model. No? So Richardson model is the contact process without cures. And it's, so for the case of exponential, it has various features because you can think of it as first passage percolation and so on. But when it's not, so the basic point for this result is that if you have your renewals with this gap condition, then even without cures, you look at your process without cures and just see the shape. I mean, we don't know the shape really, but just let's see the maximum distance that we can travel up to time t. That's called R of t. So it's the maximum norm of 1 such that there is a path from the origin to xt. So it's the same issue as then this guy grows sublinearly. So this is, let us focus on the second part here. So if mu has this gap condition, which happens under ABC, then RT has a sublinear growth. There is some rho, and this rho could be anything smaller than epsilon. Epsilon appears here in that condition, so then goes to 0. So your process grows very slowly because there are very big gaps between transmissions. No? So and I guess you can believe that it's not so obvious, no? Because there is demands of proof, but it indicates to you that since it doesn't grow linearly, at least if the cures are exponential, any delta will kill it. But it's true also for more general. But that's what is the main. And this result by itself, this sublinear growth, is proven in it's in a simple way, but I think it's also nice to say a little bit. So it's a kind of a toy model, if you want. Let us think of a P, which is small, let us say less than P critical, and you iterate percolation. So you start with a finite set V, and you look, it's connected component of V. In this, it's subcritical, so it will stop. And then you start again with an independent. So you give a new chance to the neighbors and you grow again, and so on and so on. And you see what you have after n of such iterations, and you have something what is written there. So your Rn is how far you can go after n steps. You go like something like that. Okay, and this will yield what we are saying there. Why? Well, I mean, since you have the conditions we have, it's simple to say this is doesn't use truly gap. It's just that you have, but anyway, that from gap it's trivial. That if you take an age 0 fixed and you just grow linearly, then this probability is less than, can make it as small as you wish, but say less than p critical. But taking that you can make the gaps really large, then you see immediately that at this Tn, Rtn is smaller than this because you have at most n of this ratio. And due to the just replacing there what it is, and now you see that if you take an S, which is between Tn minus 1 and Tn, your Rs is not so large, and now you just need to estimate n. But due to the fact how it grows these renewals, it's easy to check that n grows sublinearly like that. So it's the main tool here is just is this idea of using the iterated percolation. It's like you refresh, you grow and then you give chance to the border and you refresh again and so on. But it still has a growth which is just a bit, it's still below n times any logarithm of n times something. So that was, this is the idea for this part. I don't want to give all the details because I said this part you believe. I don't want to spend too much time. That if it grows sublinearly, then you will be able to stop it with any positive delta. But I'm not giving the proof here. But it's kind of, you know, at some time in a long time interval, you are going to have everything in a ball which grows less than that. And well, I mean, it's not trivial. We need to make some argument, but it's, I think, easy to believe, and I prefer to have the time to discuss others, but other issues. So the main point, I think, is that you can say something about the growth. I don't know if one can prove some shape theorem for the Richardson model in this case. Before getting to this proof, we kind of tried to use the methods of first passage percolation, but it's a bit different. So it doesn't quite go. So the other theorem, which was this one, on saying that you can survive if delta is small, no? And the condition is just that mu has a finite first moment, but we are in 2 dimension at least, so it's easier. And here it's a simple, nice proof that I can say in one slide without, and I guess everybody will understand, will believe without technical computations. So it's since you have, this is more or less what I had already before, simple from the renewal. If you have finite first moment, oops. This is finite first moment. I knew that I was going to get confused. Finite first moment and continuous, it's simple to see by renewal, simple renewal measure, that you do have this property. Given an epsilon, you find an age such that this happens. This was already mentioned by me in the previous slide. It's a simple fact. Okay, So for any epsilon, you can find an edge. Now you think of the following. Since we are in 2 dimensions, we just compare this with side bond oriented percolation. And this side bond oriented percolation will have very large probability for the side to be open and also for the edge to be open. This probability will be close to 1. But they are going to be dependent, but a finite range of dependence. But everybody knows that you can compare these measures with finite range dependence with Bernoulli, which has a p that goes to 1 if this parameter goes to 1, which is 1 minus epsilon. And how you can do it, it's in this picture, no? So you, instead of, you have your Z2, let us say Z2, you put a slope. So you think of this plane with slope h, and you say that site will be open if on this segment, which has length h, which is in blue there in the picture, you have no cure marks. No cure marks here, okay? And the cure marks could be Poisson, but could be also with another renewal and just scaled down by 1 over delta. So it's the rate delta. Doesn't matter. And on the other hand, for the errors, you are going to say that the error is open, the edge is open. If there is a connection, renewal, this renewal of the transmissions from this guy to this guy within this first part of the blue of the line, the first part. So it transmits, and now there are no cures. So in this sense, it's very simple because you don't need to use the same renewal more than once. So you don't care about all the correlation that could have or whatever when you have a renewal process. So it's just you are going to use each of them only once, and you can compare with oriented side bond percolation on Z2 in this case. So you are going to increase even in a quadrant. Okay, so it's in this sense. So the only result that we are afterwards, having seen this, having figured out this, you just need to use this comparison because you are going to have 1 minus epsilon for each of them to be open, but they are going to have a finite range of dependence, and that's okay. There is this classical theorem of Liggett, Schoeman, and Stacy that you can use. Oops, I went back. No, now I went. So for theorem 3, item 3, the ideas are very similar to what Luis Renato mentioned, so I will be very quick on that. But there are some similarities with what I want to do for theorem 3, you know, which was, so this shouldn't be 3. Yeah, 3. Yeah, 3. Okay. I don't know. The theorem on the I think should be 2, I guess. I don't know. I don't remember. The theorem on the edge renewal contact process, okay? Yeah. Theorem 2 was a theorem on site renewal, so it's okay, the number. So it says that if your measure has this a little bit more than first moment, then delta critical is finite. That means well, I mean, that's the analog of what we had already mentioned. For delta large, you get extinction. So this condition gives you extinction for delta large, not it's the analog of what Luis Renato mentioned that you have explained. You have extinction for lambda small. Of course, delta large and lambda small are companions. So the main point which I want to say, to recall here, is the bound, the only tool that we have in general is this kind of control on the gaps. No, there was from a lower bound on the gaps was this gap condition that was proven under ABC. An upper bound on the gaps comes from a moment condition. So if you have something a little bit more than first moment, you get an explicit upper bound for the gap, which is uniform. That means if you have an interval of length u, the probability of not having a renewal is bounded by this 1 over f of u. So the point is that, of course, once you have finite first moment, you can find an f that goes to infinite and for which still it's the integral. But it's going to be useless if this f grows too slowly. So it requires a little bit more. And the idea here is this renormalization, multi-scale. So you have, oops. No, you have these crossings, events that I don't need to spend time on that because they were already explained by Luis Renato. And it's very convenient to think of half crossing, just half of the box in both directions. So the event which is general is that if you have survival, you have an infinite path, no? Then you must have one of these crossings, of course. No? And I'm going to call the event age of Bn this one, that you have a half crossing in the time or in one of the space directions. You need to get out of the box. Okay? So this was used by Renato for the side bond, so that means, but it's a general thing about percolation. So it works as well as for the edge. Not just that the things are different, but it works in the same way. So, and now you want to see how we can use this for how we can use this. So basically, once you have that inequality which is there, you have a box of certain scale, and you compare survival with the crossing of the box. And then you want to say, well, if exactly what Renato said, if I have a box of a certain scale, then I have two boxes of a smaller scale, and maybe I iterated this estimate and I get something. That was the idea, and an idea which we use here, but for the contact process in a different manner. Okay, so you want to or recurse this inequality or go all the way up to the first scale and then estimate it. That's the way we kind of want to deal with it. So now let me think of the contact process in dynamic edges, because we want to prove that there is some extinction there. There we want to say, well, if P is subcritical and lambda is given, then if I take V small, it will not survive. That's the result which was mentioned there. So it is similar to what has been done by Luis Renato in terms of the statement, but the context is a bit different, so I need to give you some feeling. And one of the differences of that with respect to the case that is or the site renewal or the edge renewals that we remember case, the boxes were going super exponentially in the time direction, so here they are going to grow like that. I'm going to fix some L0, and this guy will grow exponentially, and also this one, and these rates are going to be this alpha and beta one needs to find. But what is the main point? The main point is that if I want to say that there is this half crossing of a scale n, then there will be at least 2 half crossings of scale n minus 1 inside of Bn, and they are not going to be too close to each other, these boxes, because you need some independence. Otherwise, you are not able to. You remember also in the case of that Renato mentioned, you need to separate the things. Otherwise, it's useless to estimate. And then you can think like that. That's why we want beta not to be too small and alpha not to be too small. So this is just geometric, and it's simple from the construction. It's basically the same. And the important thing, if you want to develop this, is that you need to control, or you need to control the correlations if they are far in one of these directions, or in time, or in space. And also you need to see how many you have, because afterwards you need to get to win against the number, the entropy part. Okay, so that's the way we deal with that. So there are 2 possibilities. Or you try to do exactly as what we had done before in the site renewals, and can be done also in the edge renewal, which is to iterate, to make a recursion for the maximum case. Now that was the result that Renato mentioned, goes along this line. You had an equation for un that was the supremum at the scale n, and you had some equation, and well, there was some estimate afterwards. But this, I put it like that because it sort of allows to give a general, can deal with other processes. This is a scheme for renormalization, which is quite general. It has been used in other things. No, it's like that. So there are these 2 possibilities: or you go with the first line, or you go with the second, and you have 1 box of scale. Here I change n to k. I see. Change n as scale k. You have 2 boxes of scale k minus 1. You have 4 of scale k minus 2, and so on up to the first scale, and then you are going to end up with this 2 to the k, and you have some intersection of this leaf. So there is a kind of a tree, and you go to the leaf, and that's the first scale, and you need to estimate this probability of this intersection, where all these guys will be in some sense separated, so that you are able to control the dependence, and then you need to beat this one, because the C, it's fixed, it's a constant that will depend on the scales. So that is the general method. And now I don't want to do with this, because we have used, but it's exactly the same as in the case of site. Now, do you remember that Luis Renato had this equation, something like that, that was iterating in 1 step instead of going all the hierarchical structure until the end. And what was important to be able to split, to have a product there, was that you can separate things, And that means that in his case, he had to have enough cures. Well, if we were dealing with the edge renewals, it's the same, just that you need to have enough renewals for the edges, because the point is that the renewals separate things, make them independent. So we can use it's exactly the same proof for the edge renewals. Just that not enough cures, but renewals. And you have these boxes, which are not boxes of n-1 scale. They are too thick but then you, by simple geometric things, you get a factor here, and you control this this kind of from n to n minus 1. That was already done by Renato, and we can use the same for one of those items in theorem. I don't know, the edge renewal, I think it was called 3. Okay, so that was a general thing you make, and that's from where that condition on F came, so that this converges, you get something, and then Renato had to take lambda small to make the first one small, and for us, it's just the same that you need to take delta large, but it's the same. Okay, so these are, it's not fun to go back again because it's the same. Now for the, I need to say something, it's about the contact with dynamic edges that I want to prove. The first part of our theorem there, if P is subcritical, and as V goes to 0, lambda critical goes to infinity. That means fix a P subcritical, fix a lambda, finite, show that for V small, it will not survive. So that's what I want to focus. That was, so it uses the same similar structure of renormalization, multi-scale, but it's a bit different in the way how to perform the estimates. So we take a P, a lambda, and want to find that V0 so that if V is less than V0, then dies out. So you don't care too much. I already said that alpha had to be a bit big, beta also, because you want to have two pieces which are separated. That's clear that you cannot be too small. And you give a delta to U so that even if you have to pay something to compare with your process, by increasing by delta, it's like increasing a bit your percolation, you still are below P critical. So delta is something small that even if you add it, it doesn't go above, it stays below P critical. And you also want your bit beta is such that it allows for the cures to happen so that you renew. So this condition is that small is the probability that you don't have a cure there because it's to renew. Okay, now you have these parameters, and we set this multi-scale scheme. So I just have to tell what is L0 and B0 because we have fixed V in terms of age. So V goes to 0 when age gets large. But our theorem is just that for V small enough. So it's enough that we take a B0 large enough that the thing collapses, that doesn't percolate. So we have this scheme which I mentioned. You have these boxes of scale K, and they are given by this alpha L0. Alpha, no, this LK grows with alpha, and this goes with beta. And I developed them up to the end. And so when you get to scale 0, you are going to simply have your rectangles of first scale. So they will have a height B0, and they will be located somewhere, but you can examine them in an increasing order by time. So that's the way we do. So we develop all the, up to the end, you have all these 2 to the k boxes, and you want to see that the probability that to have the intersection of half crossings in all of them decays to 0 faster than it compensates the entropic factor that you had, which was C to the 2 to the k. And how we do that, how we do that. Well, so you have this what I call their leaves. They are just these rectangles of first scale, L0, and you want to control the probability that there have crosses in all of them, that intersection of crosses. So I'm looking in one rectangle, and I want to say to control the probability to have a crossing condition on all those which are below. No? So in order to get an estimate of the conditional probability, we could do the following. We can do the following. We are going to say, so P of Lj is just the floor of your interval, in the bottom timeline, in the bottom of the line. So an edge there, I'm going to say, if it opens during the whole thing, we are going to call it open in the beginning. If it doesn't update a little bit below, which was in this piece, which is this margin to separate the boxes, it does not update there, we also include it. And if it updates and it's open at the beginning, we also include it. So we get something which is bigger, but we pay a price, but we don't need to worry about those which are below. It will be independent. So, and the price we pay, there is something wrong there. It's not a P here. It's a delta, of course. This is a delta. No, wait. Well, P is the, no, yeah, it's delta. No? Well, anyway, I had a P, which it's here, which is wrong. It's PC. No, it's the average. No, it's the average between, yeah, it's okay. It's not wrong. It's less than P critical. My P is less than P critical, and I take the average, so it's less. And the event that we consider is a bit bigger than the one we are interested. So I'm going to say that the event H hat occurs if there is a half crossing in your rectangle for the process that starts with this, the whole P of Lj for all these edges which I allow here. So, no, because your cluster is subcritical. So whatever it is, you have some small pieces open. But you consider everything there, all the sides of this interval. And the edges are these which are available in the beginning. But then you freeze everything. So you don't care about what was below, and everything is, and so in this way, you don't have any dependence. So it's enough that you control this probability of this event. So what is that? You have a contact process in a rectangle, which has a width L0 and has a height L0, B0, and you want to say that you can take these guys, L0 and B0, in such a way that this probability will be small as you wish. Well, I mean, the contact process in a finite set, you know a lot about it. You know something, how long it survives, it dies, but how long it takes to die, and so on. So you can prove that you can take L0. L0 has to be, because when L0 is large, it depends on L0 will be large, and B0 will be much larger than L0. If you take them suitable, you make this probability arbitrarily small. So that's the way. So everything else was already fixed. So you just had to take these two guys, and you can do it by examining the contact process. The other part, which was if P is supercritical, then your lambda 0 is bounded. It's a completely different argument. Is a one-step renormalization. After you examining what is the supercritical percolation restricted to a large box, and then So you can compare it with by making suitable only one step renormalization, compare with oriented percolation with a finite range of dependence. So it is a different different thing, and it's maybe, well, it depends on the nice behavior of the percolation, but I don't want to enter because it's too much time, and I put here the references, and thank you. So I think I went a bit.
Thank you, Eulalia. Any questions? Okay.
Thanks for a nice talk. Suppose you conditioning, you have a path which survives. You have percolation. Can you say how many you got at the path, the unique or
How many?
Yeah, suppose you have a percolation, you would have an infinite path. Can you say the probability after, say, a certain time, you're very close to this percolation with a certain probability, other passes?
To say something on the
Yeah.
percolation density. You
Yeah,
mean?
yeah.
Well, I think the proofs give something, but I don't believe it's so good. Because you see, these questions that we are dealing are just like eliminating one of the trivial sides to say that there is subcritical region or there is supercritical region is still too. So yeah, the proofs give something, but I don't believe they are anything. But anyway, it's very hard to get anything sharp, even for the contact process to have a sharp estimate on. But I'm not understanding if you want about the parameter or about, yeah, it's about the parameter that you asked. The function percolation, the percolation density.
This conditioning survival and how they look like.
Yeah, well, something comes out of the proofs, but I don't think it's so good. And yeah, I don't think as estimates they are so good, but there is something.
These are very difficult. What if you have more than two states? Can you do that? Intermediate state.
So you might have infection of one type or of another type, you mean?
Or somebody who's infected but not detected. No,
Yeah,
something
could be.
serious infected by somebody in between. Can you do that?
That would
Must be very hard.
No, the thing which we try to think is when you have environments which have some interaction, because here our environments are totally independent.
Yeah.
And it's, if you think of anything more applied, then it's natural to think of them as having some interaction, like the environment being exclusion process that individuals that move or move around, and if they are together, then there is possibility of transmission, otherwise it's not.
Oh, that's very
This one we are dealing with it, but more general. I say when there is some competition also, I think you want to say that. You might have infection of one type or of another type, and one is preponderant with respect to the other one. No? Yeah. I don't know. Yeah, for multi-type contact process, like if everything is Poisson, but just that they are different types of infections, then there are these Claudia Neuhauser, classical, and also more recent papers. But here, yeah, it's interesting. I think it's an interesting issue, but I don't know.
Any more questions?
So I was thinking about a sort of discrete version of your model, on which, for example, the arrows are at half integer points and the renewals at integer points. So it seems that for your techniques, is that those cases also apply. Maybe the proofs are even easier than the continuous case, no?
Yeah, well, I mean, for the case of site percolation, site renewal, we had dealt with mu discrete, though we didn't insert in the paper, but with the mu is arithmetic. So it gives some discrete process, even if the infections, the cures could be. But here we didn't think about it. Yeah, I think you can do, just that you need to put things a little bit different. Because here you say if you have an atom at 3, and this atom is maybe subcritical, but now you combine 2 3s at a time 6, everybody gets, you get an infinite cluster, then you maybe collapse some part of it, but it stays infinite all the time. So it will be.
And the other question is about your comparison with the Richardson model. It's so the result that you use for the Richardson model, I haven't seen them in the literature, so you had to reprove some of the stuff to apply it here.
No, we gave it this name Richardson mu because it's the same as Richardson, but just that instead of having exponentials in interarrival, it's another measure, mu. So we call it Richardson model, but we didn't find anything about it.
Yeah.
At least as far as I know. So that's why I thought that that proposition which I mentioned there is interesting by itself. We included it because didn't know much. But yeah, it would be nice to prove more, say, because here the philosophy was to have this general thing, to be able to say when you are in then if you take mu with reasonable, a measure with a good tail, then of course this process is not Markov, but you can say a lot about it. You can say, I think that's why it would be interesting to have students working on this kind, because for instance, metastability is an issue that it would be nice to have a description of metastability for stochastic dynamics when it's not Markovian and this exponential time emerges anyway. So I think it's nice, but so far we are now what we are thinking is this more different, more general environments when you have interaction. And an issue which I didn't mention at all here is about lambda critical being finite in the site percolation, site renewal. So it should be quite general, but still the kind of theorem that we have is still not general. And the reason is this: it's difficult to compare two processes. You take one with mu, another with mu prime. Can you compare them? I mean, it's easy to compare when one of them, when they have density and have a decreasing failure rate, things like that. But in general, it's not, because when you have a decreasing hazard rate, then it's very easy to compare the process with construct the process on the top of Poisson point process. So you do have many ways to, I mean, and this has been used a lot by people in applied things, you know, this construction, but we don't know.
Yeah.
Okay, let's think of.
So what
Sure,
may I?
sure.
So the conference ends tomorrow, but I think long lectures. The last, it's I think my honor to now. I think it's the good time for us to give a very big applause to the organizer and to everyone who was invited or involved in the organization of this very nice conference. They really did a great job.
you have a very good night. Eu acho que ele desliga, só para apertar.
Ele desliga. Aperta um pouquinho.